Hello there and welcome to Physics with William, where curiosity gets comfortable and science takes its time. Tonight we're settling in with a question so large that it sits quietly behind almost everything you have ever seen, touched, or wondered about. What is actually holding the universe together? It is the sort of question that sounds simple at first, almost like something a child might ask while looking up at the night sky. And yet the longer you sit with it, the stranger it becomes. Because when you really think about it, nothing is under any obligation to stay where it is. The planets do not have to keep circling their stars. Stars do not have to hold themselves together against the enormous violence inside them. Galaxies do not have to keep their shape. Atoms do not have to remain intact. Even you, sitting or lying there right now, are made of parts that in some sense ought to be restless, eager to move, spread out or fly apart if not for certain rules and relationships that keep everything in some kind of order. And before we get too far into that very large and slightly unsettling thought, I would love to ask you something small and personal. Where are you listening from tonight? What part of the world is holding you at this moment? And what kind of hour is it where you are right now? Perhaps it is late and the house is quiet. Perhaps there is rain tapping at the window. Perhaps the day has only just begun for you, and this is your moment of calm before everything starts moving again. It feels fitting somehow, a question about what holds the universe together, while each of us listens from our own little patch of it, held in place by a chair, a bed, a floor, a city, a planet, a star, and all the invisible rules that keep this great structure from dissolving into nonsense. If you find this soothing, or interesting, or simply a gentle way to wind down after a long day, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this quiet little corner of science find its way to other people who might enjoy a slower kind of wonder. And now let us ease into the question itself, because once you begin pulling on this thread, you discover that almost everything in reality is, in one way or another, an answer to it. It is easy to look at the world and assume that togetherness is the natural state of things. A table stays a table, a mountain stays a mountain. The moon goes on circling the earth as if it has signed a very old contract. We grow up surrounded by stability, or at least by stability that is good enough for daily life, and so we rarely stop to ask why things do not simply come apart. But if you could zoom in far enough, or step back far enough, you would see that holding together is not automatic at all. It is something that has to be achieved. Sometimes it is achieved through attraction, sometimes through balance, sometimes through a kind of compromise between competing tendencies. The universe is full of things that remain intact only because different influences are constantly pushing and pulling in just the right ways. Take something as ordinary as your own body. It feels solid enough. Dependable, most days. But the material you're made of is mostly empty space if you look deeply enough. Atoms themselves are not tiny little pebbles packed neatly together like beads in a jar. They are structured, dynamic systems with components that would make very little sense to our everyday intuition. The matter in your hands, your face, your bones, your heartbeat, is not held together by obvious hooks or strings. It is held together by interactions that are invisible to the eye and deeply strange once you begin to examine them. What feels firm is, at a more fundamental level, a carefully managed arrangement. That is one of the first uncomfortable and fascinating truths about the universe. Stability is not simplicity. A calm-looking thing may only be calm because a tremendous amount of activity is being balanced beneath the surface. A star looks serene from a distance, a quiet point of light pinned to the night, but inside it there is pressure, heat, collision, and struggle on an almost absurd scale. A planet seems steady underfoot, but it is falling through space while spinning, bound to a star that is moving through a galaxy that is itself drifting through a far larger structure. Even an atom, that old textbook symbol of neat scientific certainty, turns out to be less like a miniature solar system and more like a set of relationships that only behave sensibly when described with ideas that most of us would not naturally invent over breakfast. So perhaps a better way to ask our question is not simply what holds the universe together, but how does anything remain itself at all? Why does a thing continue to be the thing it is, rather than becoming something else, or scattering into its ingredients, or never forming in the first place? Why do particles bind into atoms, atoms into molecules, molecules into rocks, oceans, clouds, carrots, cats, and people who listen to sleepy science videos in bed? Why do stars not explode the instant they ignite? Why do galaxies not shrug their shoulders and let their stars wander off in every direction? Why is there enough order, enough persistence, enough structure for a universe like ours to tell a story instead of just making a mess? In daily life, when we say that something is holding something else together, we usually mean it in a very physical and obvious way. Glue holds a broken vase together, a belt holds up a pair of trousers, a shelf bracket holds up a shelf, assuming it was installed by someone reasonably competent. These are mechanical kinds of support. You can point to the thing doing the holding, you can touch it, you can often replace it when it fails. But in the deeper layers of physics, holding together usually means something subtler. It means that the behaviour of matter and energy is such that structures can persist. It means that certain interactions encourage clumping, binding, orbiting, or mutual dependence. It means that what could drift apart does not, because reality is built in ways of making relationships stick. That word relationship matters more than it might seem. At the most basic level, much of physics is not really about objects in isolation. It is about objects affecting one another. A single particle alone in a featureless void is not very interesting for long. The drama begins when one thing influences another, pulls it, deflects it, binds to it, exchanges something with it, changes what it can do. The universe, in that sense, is less like a pile of separate bricks and more like a web of ongoing connections. Things stay together not because they possess some magical inner stubbornness, but because they are caught up in patterns of interaction that make togetherness possible. And yet not everything in the universe is trying to gather. Some things in a way are trying to spread out. Heat spreads, gas expands. Explosions do what explosions famously do. Stars pour radiation into space. The universe itself, on the largest scales we can observe, is expanding. There is no universal rule that says things must clump neatly and remain where they are put. Quite the opposite. Left to certain conditions, matter will disperse, energy will move, and systems will drift towards states that are less organised. So whenever we find structure, whenever we find a stable object or a long-lived arrangement, there is usually a reason. Something is countering the tendency to fly apart. Something is giving order enough leverage to resist chaos for a while. That phrase "for a while" is worth keeping in mind. Because one of the quiet lessons of physics is that holding together is often temporary. Mountains erode, stars burn through their fuel, atoms in radioactive materials eventually change. Orbits shift, galaxies collide. Even the seemingly permanent is often just the very patient. The universe does not hand out eternal guarantees. What it offers instead are timescales. Some structures last for fractions of a second, others endure for billions of years. To us, anything that survives longer than our own brief lives can feel practically immortal. But physics is not especially sentimental about duration. It simply asks what processes are in balance, how long that balance can last, and under what conditions it will fail. This makes the universe sound rather precarious, and in some respects it is. But it is also astonishingly good at building stable arrangements when the rules allow. There is a kind of practicality to nature. Given the right ingredients and conditions, matter finds ways to settle into patterns. Electrons bind to nuclei. Atoms share or trade electrons and become molecules. Gas clouds collapse under gravity and form stars. Stars forge heavier elements. Those elements become planets and oceans and atmospheres and chemistry. rich environments where more complicated things can happen. None of this requires intention. No one is up there carefully bolting galaxies together with a cosmic wrench. What exists instead are laws, tendencies, and interactions that make some outcomes more likely than others. The universe is not assembled like furniture. It is more like a long history of what matter does when the rules are what they are. Now, if you have ever built a tower out of books or tried to stack groceries in a refrigerator that was already one yogurt away from disaster, you know that keeping things together often means balancing competing demands. Too much weight in the wrong place and the whole arrangement becomes a cautionary tale. Too little support and collapse follows. The universe works in a similar way, though with better engineering and fewer dented tomatoes. Stars, for example, exist because gravity is trying to crush them inward, while pressure from the hot material inside pushes outward. If either side won completely, the star as we know it would not exist. A stable star is not a simple thing. It is an ongoing negotiated settlement between collapse and expansion. Many structures in the universe are like that. They persist not because nothing is happening, but because opposing influences have found a way to coexist for a time. There is also something humbling in realizing how invisible most of this is to us. We do not wake up each morning thinking about the forces that keep our feet on the ground, our atoms intact, our planet in orbit, and our star from blowing itself apart before breakfast. We are wonderfully insulated from the deeper strangeness of reality by the very success of that reality at maintaining itself. The floor does not need to explain itself every day. The sky keeps its distance. The Earth does not send a formal notice that it remains in orbit for another year. We live inside a working system, and because it works so reliably at our scale, we are free to forget how remarkable it is. Still, the question waits. What is actually doing the holding? Is it one thing or many? Is there a single deep answer underneath all the others, or is the universe more like a patchwork of different kinds of togetherness, each operating in its own domain? The gentle truth is that there is no one universal glue. The cosmos is not held together by a single mechanism that applies in exactly the same way everywhere. Instead, different scales of reality are governed by different interactions. What holds a galaxy together is not quite what holds a star together. What holds a star together is not quite what holds an atom together. What holds an atomic nucleus together is stranger still. And as we move from the vast down to the tiny, the universe begins to reveal that its stability is layered. Reality is not one knot, but many knots, tied at different levels, in different ways, with different consequences. This layered structure is part of what makes the subject so satisfying. You can begin with the night sky, with stars and planets, and the grand architecture of the cosmos, and then travel inward toward the familiar solidity of stones and skin, and then farther still into the hidden interior of matter, where the rules become less intuitive and far more interesting. At every stage, the same question returns in a new form. Why does this stay together? What stops it from falling apart? What allows this arrangement to exist longer than a heartbeat? And at every stage, the answer becomes a little more revealing, not just about the object in question, but about the character of the universe itself. There is another reason this question matters, and it is not just scientific curiosity. When people first hear phrases like the laws of nature or the forces of physics, it can all sound a bit remote, as though these are topics that live in textbooks, laboratories, or documentaries narrated in a reassuring voice after midnight. But the truth is more intimate than that. The reason your chair supports you, the reason your lungs work, the reason the Earth circles the sun rather than wandering off into the black, the reason stars can shine long enough for planets and life to appear, all of it belongs to this same story. Asking what holds the universe together is really asking what makes any continued existence possible, why there is persistence instead of instant dispersal, why there is form instead of only motion, why the world has enough coherence for anything, including you, to last long enough to notice it. And perhaps that is where the wonder really begins. Not in the fact that the universe is large, though it certainly is. Not even in the fact that it is old, though it has had an impressive amount of time to practice being itself. The deeper wonder is that it is coherent, that there are rules, that those rules allow structures to emerge and remain, that a cosmos filled with movement and energy and change can nevertheless produce stars that burn steadily, planets that orbit predictably, elements that combine reliably, and living creatures that can ask how any of it works in the first place. Of course, the moment you begin to admire that coherence, the next question starts nudging at the door. If everything depends on these different ways of holding together, why do some things still come apart so readily? Why does a star eventually die? Why do atoms sometimes decay? Why does the universe allow both stability and collapse, both structure and dissolution? The answer, as we will ease into next, is that holding together is never the whole story. Every stable thing in the universe exists in conversation with forces that could undo it. The drama of reality is not that things simply stay together forever, but that they hold together under pressure, under motion, under change, sometimes beautifully and sometimes only barely, and that the balance between staying whole and coming apart is what gives the universe so much of its character. At first glance, it may seem as though drifting apart ought to be the natural fate of everything. If you watch a puff of smoke rise into the air, it spreads. If you spill a drop of ink in water, it swirls outward. If you leave a room untidy for long enough, order seems to give up the fight and retreat quietly into some distant corner of the universe. Things scatter, they loosen, they spread out. So it is worth pausing over a very simple and very strange observation. The universe is full of things that do not do that, or at least not right away. Stars remain stars for astonishingly long spans of time. Planets keep circling. Galaxies do not immediately dissolve into lonely wandering suns. Atoms stay intact. Mountains, tables, oceans, and people manage to remain themselves long enough for memory, history, and lunch plans to exist. And when you really sit with that fact, it becomes a little mysterious. Why does not everything simply drift apart? One reason the question feels so natural is that drifting apart is easy to imagine. It asks very little of the world. You can picture a cluster of marbles rolling away from one another if nothing stops them. You can picture a crowd dispersing after a concert, everyone peeling off in their own direction. You can picture warmth leaking from a cup of tea, its heat gradually sharing itself with the cooler air until the whole arrangement becomes less dramatic and more evenly dull. Spreading out feels ordinary. Staying together begins to look like the real surprise. In a sense, physics agrees. There are many situations in nature where spreading out is exactly what matter and energy prefer to do. Gases expand to fill the space available to them. Heat moves from warmer places to cooler ones. Explosions throw material outward. Light races away from its source. Even on the larger scales, the universe itself is expanding, with distant galaxies carried farther and farther apart by the stretching of space. The cosmos is not a place where everything huddles together by default. Quite often it's a place where distance grows, differences soften, and concentrated things become less concentrated. And yet here we are, in a world of structure. You're not an expanding fog. The bed or chair beneath you is not slowly dissolving into the room. The earth is not leaking away from under your feet like steam from a kettle. The moon has not wandered off out of boredom. Something, clearly, is working against the general tendency of things to spread. Or perhaps more accurately, several somethings are working against it, each in its own domain, each at its own scale, each giving form and persistence to a universe that might otherwise have been far thinner, simpler, and much less interesting. It helps to begin by noticing that togetherness in nature is rarely free. When something remains whole, some balance has usually been struck. Some influence is countering another. Some rule is favouring closeness over separation. In everyday life, we often do this without thinking. A knot keeps a parcel closed because the tension in the string resists being pulled loose. A building stands because the materials in it can bear weight without collapsing. A spinning top stays upright for a while because its motion gives it a kind of stability that stillness would not. The principle is often the same in deeper physics. A thing stays together because the conditions permit a stable arrangement, not because the universe has a sentimental attachment to neatness. That idea of stability matters. When physicists speak about something being stable, they usually do not mean eternal or indestructible. They mean that under the circumstances the thing can persist. It has found a state that does not immediately unravel. A rock resting in a valley is more stable than a rock balanced on a narrow ridge. One can stay put for ages. The other needs only the smallest nudge to become a cautionary tale. Nature is full of systems that settle into states where change becomes less urgent. The interesting twist is that these stable states can look very different depending on scale. A planet in orbit is stable in one way, an atom is stable in another, a galaxy is stable in yet another. But in each case, the deeper story is the same. The arrangement lasts because the rules allow it to last. There is also a temptation to imagine that if something is held together, it must be still inside, calm at its core, quietly resting in a state of cosmic contentment. Very often the opposite is true. Many things persist not because nothing is happening, but because many things are happening at once in a balanced way. Consider a star. From Earth, it looks like a small, steady point of light, perhaps even a serene one. Yet a star is not serene in any ordinary sense. It is a place of immense pressure and heat. Gravity is trying to compress its mass inward, while the violent processes in its interior create pressure that pushes outward. The star exists because these tendencies oppose one another with extraordinary precision. If the inward pull won completely, collapse would follow. If the outward push dominated, the star would tear itself apart. Its long life depends on a dynamic balance, a continuing negotiation rather than a peaceful truce. The same kind of logic appears again and again. The Earth circles the Sun not because it is nailed to some invisible track, but because motion and gravity work together in just the right way. If gravity vanished, the Earth would move off into space in a straight line. If the Earth were not already moving sideways through space, gravity would draw it inward far more directly. Orbit is what happens when falling and missing combine into something elegant. Our planet is, in a sense, always trying to fall toward the Sun, and always moving in such a way that it keeps missing it. The result is not drifting apart and not crashing inward, but a lasting pattern that feels almost inevitable once you're used to it. This begins to reveal something important about the universe. A great many lasting structures are not explained by a single simple answer. They exist because several ingredients come together at once. Motion matters, distance matters, mass matters, energy matters. The specific properties of particles matter. The geometry of space matters. Once you stop looking for one universal glue and start looking for the conditions under which stability becomes possible, the world begins to make more sense. Still, it also becomes stranger, because the kinds of stability we rely on every day turn out to rest on rules that are not at all obvious from ordinary experience. For instance, imagine holding a small object in your hand. It feels solid, simple almost. But what you're actually feeling is a story about resistance. The atoms in your hand and the atoms in the object do not merge into a blur. They do not pass through one another like mist. They keep their distance in a highly organized way. The solidity of matter, one of the most familiar facts in life, is already an answer to the question of why things do not simply drift apart, though it is also an answer to why they do not simply collapse into each other. The universe, annoyingly and wonderfully, is often doing both jobs at once. It stops some things from flying apart and other things from crowding together too much. Order lives in that middle ground. This is why the image of the universe as a kind of giant machine can be helpful only up to a point. Machines suggest rigid pieces, clean joints, obvious causes, but the real world is more subtle. It is a place of tendencies and constraints, of preferred arrangements, of motions shaped by invisible rules. Much of what stays together does so because there is a lowest effort way for it to exist, a configuration that is in some sense easier for nature to maintain than the alternatives. A ball rolls downhill rather than uphill because that direction is simpler for gravity. Hot tea cools rather than grows hotter on its own because the spreading of heat is more likely than its spontaneous reconcentration. Likewise, atoms and stars and planets find ways of being that are not random. They settle where the underlying rules make persistence possible. Of course, not everything stays together forever. This is where the question becomes especially interesting. If the universe has so many ways of making structure, why does it also allow structure to fail? Why do stars die? Why do cliffs crumble? Why do molecules break apart? Why does a warm loaf of bread eventually go cold and disappointing? The answer is that stability is always local. It belongs to particular conditions. Change the conditions, and the balance may no longer hold. A snowflake is stable in cold air and not in a hot oven. A star is stable while it has the right internal processes available, and not after they are exhausted. A planet can keep an atmosphere under one set of circumstances and lose it under another. Togetherness is real, but it is not unconditional. There is a broader principle here that physicists often return to in one form or another. The universe permits structure, but it does not promise permanence. What it offers are processes that can resist dispersal for a while, sometimes for unbelievably long whiles, but never in a way that frees them entirely from change. This can sound a little bleak if taken in the wrong mood, but it is also what gives the cosmos its richness. If everything stayed exactly as it was forever, nothing interesting could happen. No stars would evolve, no elements would be forged, no planets would cool, no chemistry would unfold into biology. Change threatens structure, yes, but it also makes new structure possible. The same universe that allows things to drift apart also allows parts to come together in new and astonishing ways. In fact, one of the deepest patterns in nature is this constant interplay between dispersal and gathering. Clouds spread, then condense. Gas drifts, then collapses under gravity. Stars blow material into space, and that material later becomes part of new stars and planets. Even life itself depends on this tension. Your body maintains order only by constantly exchanging matter and energy with its surroundings. You breathe, eat, release heat, repair, replace, rebuild. You're not a statue resisting time through stillness. You're a process holding together through activity. On some level, most of the things we think of as stable are like that. Their persistence is not the absence of change, but the management of it. This is perhaps one of the most useful ways to think about why everything does not simply drift apart. We are not living in a universe where the default is stillness and occasional motion disrupts it. We are living in a universe where motion and change are everywhere, and stability is something achieved within that motion. A whirlpool in a river is not a solid object, yet it has shape and continuity. It lasts because the flow supports the pattern. In a much grander and more varied way, many cosmic structures are like that. Their lasting form comes from the very processes that might seem at first likely to destroy them. Even so, it is hard to shake the intuition that things ought to separate. After all, if space is so vast and matter is surrounded by emptiness, why is clustering so common? Why stars at all? Why planets? Why galaxies? Why not just a thin, dull mist of particles drifting ever farther from one another in an indifferent dark? Part of the answer is gravity, which we will linger with more fully later, but even before naming it in detail, we can appreciate the general point. The universe contains ways for matter to notice matter, ways for one thing to influence another across distance. That alone changes everything. A cosmos where things affected only themselves would remain a lonely scatter. A cosmos where things can pull, bind, attract, resist and respond becomes a place where structure can emerge. And once structure begins, it often encourages more structure. A star forms, and now it can warm planets. A heavy element is made inside that star, and now new kinds of chemistry become possible. A planet forms with liquid water, and now complexity has a stage on which to improvise. Holding together is not just about preventing disaster, it is about making further stories possible. It is about continuity, about giving reality enough memory to build on what came before. A universe where everything instantly drifted apart would have no biographies, only momentary flashes. There is something quietly reassuring in that, though perhaps reassuring is not quite the word. It is more that the universe begins to seem less arbitrary. The stability around us is not a lucky accident repeated endlessly for our convenience. It is built into the way nature behaves. Not uniformly, not always gently, and not without eventual endings, but deeply enough that stars can shine for billions of years, and atoms can endure long enough to become poems, limestone, and sleepy listeners under blankets. The world is not precariously one breath away from coming undone for no reason at all. It is held in countless ways, at countless levels, by rules that favour patterns over pure dispersal. That does not mean the question is finished. Far from it. Once you accept that things do not drift apart because the universe has mechanisms for binding and balance, the next curiosity arrives almost immediately. What are those mechanisms in the ordinary world right around us? Not in the far reaches of galaxies just yet, and not deep inside atomic nuclei either, but in the immediate landscape of everyday reality. What holds a stone together? What makes a drop of water cling to itself? Why does metal keep its shape? Why does wood resist your hand when you press against it? Why can matter be hard, soft, liquid, brittle, flexible, smooth, rough, elastic or firm without simply dissolving into formless dust? Because once you begin to notice it, the hidden bonds of the everyday world are doing a tremendous amount of work very quietly, and they deserve a slower look. When most people hear the phrase "what holds the universe together," their minds go first to the very large. They picture stars, planets, galaxies, perhaps some grand cosmic force quietly keeping the heavens from slipping into disorder. And that instinct makes sense. The sky has a way of encouraging large thoughts. But there is another place to look before we return to those vast distances, and it is much closer than the stars. It is the world directly around you, the fabric on your sleeve, the cup on your bedside table, the floor beneath the walls of your room, the glass in a window, the water in a kettle, the wood in a chair, the skin on your hand. All of these ordinary things are made of matter that holds its shape, keeps its character, and behaves with a kind of reliability that is so familiar we almost stop noticing how strange it is. A chair does not have to be a chair, not in any deep cosmic sense. The atoms inside it could have existed in some looser arrangement, some drifting cloud of particles, some substance too soft to support weight, or too brittle to survive being sat on by a sleepy human and a medium-sized cat. Water does not have to gather into droplets. Metal does not have to feel hard. Rubber does not have to spring back after being bent. Bread does not have to have a crust, while soup does not have to remain politely liquid. Yet all around us matter takes on form after form, each with its own texture and behaviour, each revealing that the world is full of hidden bonds quietly doing their work. If you press your fingers against a table, it feels solid, immediate, unquestionable. There is resistance, is. A clear message from the universe that this bit of matter is here, and that your hand is not invited to pass through it. We take that firmness for granted, but what you are really encountering is not little billiard balls packed tightly together like fruit in a market crate. Matter at the smallest scales is nothing like our ordinary intuition would suggest. Most of an atom is empty space by volume. That phrase gets repeated so often it can start to sound like a clever fact one says at parties before someone changes the subject to biscuits, but it remains genuinely astonishing. If atoms are mostly empty space, then why do things not feel empty? Why does a table not behave like a fog? Why does your hand not glide through it like a ghost with an appointment to keep? The answer lives in interactions, in patterns of attraction and exclusion, in the behaviour of charged particles, and the rules that govern where electrons can and cannot comfortably exist. It is not that the table is secretly packed solid all the way through in the way our senses report. It is that the matter in your hand and the matter in the table respond to one another in such a way that overlap is strongly discouraged. The result is solidity, and solidity is one of the most convincing illusions reality ever produces. Not illusion in the sense that it is fake, because the resistance is quite real, and your toe will confirm this eloquently if introduced to a table leg in the dark. But illusion in the sense that the deeper picture is more subtle than the everyday feeling suggests. The world of everyday materials is really a world of electrons arranging themselves around atomic nuclei in structured ways. These electrons are not merely decorative extras orbiting politely at the edges. They are central to the character of matter. They determine whether atoms cling to one another, whether a material conducts electricity, whether it bends, stretches, dissolves, freezes, melts, or gleams in the sunlight like it is very pleased with itself. Much of the visible and tangible world is the story of how electrons are shared, traded, localized, or allowed to roam. Take something as simple as a glass of water. Water seems straightforward, almost boring in its reliability. It pours, it wets, it freezes into ice and boils into steam and generally behaves like a substance that has no interest in being mysterious. But water is one of the great masterpieces of hidden bonding. Its molecules are shaped in a way that gives them a slightly uneven distribution of electrical character. One side is not quite the same as the other. That unevenness allows neighbouring water molecules to attract one another in a specific and important way. Not as strongly as the deeper bonds holding each individual molecule together, but strongly enough to matter in every puddle, drop, cloud, river, and cup of tea on Earth. Because of this, water clings to itself. It forms droplets, it creeps into narrow spaces, it beads on some surfaces and spreads across others. It takes more energy to heat than many other substances, which helps oceans moderate climate and helps your bath lose its warmth, with disappointing patience rather than immediate cruelty. Ice floats because the arrangement of water molecules in the solid state is more open than in the liquid state, a fact so peculiar and important that whole ecosystems depend on it. Lakes freeze at the top first. Fish continue their fish-related business below. Winter becomes survivable rather than final, all because of hidden bonds between very small particles that most of us never think about while filling a kettle. Then there is metal, that wonderfully confident material that feels as though it has no doubts about being metal. A spoon is a spoon in such an unmistakable way. It is cool to the touch, hard, strong, able to ring when struck, able to bend a little without shattering, able in some cases to carry electricity as if messages and power have found a fast lane built just for them. Metals behave this way because their atoms are bonded in a rather communal manner. Instead of each atom clutching its outer electrons possessively like a dragon guarding a modest but meaningful hoard, metal atoms allow certain electrons to move more freely through the structure. The result is a kind of shared electronic environment that binds the atoms into a lattice while also granting the material many of its familiar traits. It is one reason metals can conduct electricity so well. It is one reason they can often be shaped without breaking. Their bonds are strong, but not in the rigidly fussy way that would make them snap at every inconvenience. Compare that with something like salt, which looks so innocent sitting in a shaker, and yet is built from a very different kind of arrangement. In substances like salt, atoms become charged partners by transferring electrons rather than sharing them. One type gives, the other receives, and the resulting opposite charges attract. This creates a repeating structure, neat and stable, the sort of arrangement that makes salt crystals possible, and also makes one regret spilling them into electronics. These bonds are effective, but they also lead to brittleness. Strike a crystal the wrong way, and its ordered structure can split rather neatly. Strong does not always mean tough. Stability comes in different flavours, and then there are the materials of life, which are held together by combinations of these bonding patterns in endlessly inventive ways. The proteins in your body do not owe their shape to one simple type of glue. They fold and twist because of many interactions working together. Some parts attract water, some avoid it, some are drawn to one another, some repel, some form temporary associations, some lock into more durable arrangements. Biological structure is often less like a brick wall and more like a careful choreography. The shape of a protein matters because shape determines function. A slight change in folding can change what the protein does, what it binds to, whether it works at all. Life depends not merely on atoms being present, but on them being held together in very particular ways. This is one of the quiet miracles of chemistry. The world is not made only of ingredients, it is made of arrangements. Carbon, hydrogen, oxygen, nitrogen, and a handful of other elements can produce an absurd range of substances depending on how they are bonded. The same broad family of atoms can become sugar, wax, poison, perfume, leaf, feather, muscle, soap, or the paper in an old library book that smells faintly like time and dust. What changes is not merely what atoms are involved, but how they are connected and how those connections allow larger structures to form. Carbon deserves a brief moment of admiration here, because it is almost comically versatile. It can bond in multiple directions and build chains, rings, sheets, and elaborate frameworks. This flexibility makes organic chemistry possible and gives life much of its material richness. Carbon can be part of the softness of charcoal or the extraordinary hardness of diamond, which is a lovely reminder that the same element can produce wildly different realities depending on the hidden bonds and structures involved. A diamond is not hard because carbon has decided to become morally firm. It is hard because its atoms are linked in a rigid three-dimensional network that resists deformation with impressive stubbornness. Graphite, by contrast, is also made of carbon, yet it is soft enough to leave marks on paper. Same element, different arrangement, entirely different experience. The universe is very fond of proving that structure matters. The same lesson appears when we think about the difference between solids, liquids, and gases. These are not merely labels for how substances happen to feel on a given day. They reflect how tightly particles are bound, how freely they move, and how much energy is jostling through the system. In a solid, the particles are arranged in ways that keep them in relatively fixed relationships, even if they still vibrate. In a liquid, the bonds and attractions remain important, but the particles can slide past one another. In a gas, the particles move far more freely, with much weaker constraints on their positions relative to each other. Heat can push matter from one state toward another by altering the balance between motion and bonding. Warm a solid enough and its structure loosens into liquid. Warm that liquid further and it may become gas. Cool things down and the reverse can happen. Everyday matter is constantly revealing that holding together is not all or nothing. It is a matter of degree, of conditions, of balance between energy and attraction. Even something as mundane as friction belongs to this story. When one surface rubs against another, the resistance you feel is not just a macroscopic inconvenience invented to make moving furniture more dramatic. It arises from interactions between the surfaces, from tiny irregularities, from electromagnetic effects, from the fact that matter is not perfectly smooth or indifferent. Friction is one of the reasons you can walk without immediately performing an unplanned slide across the room. It lets tyres grip roads and pencils write and violin bows coax sound from strings. It also steals energy and turns it into heat, which is less welcome when trying to move a sofa, and more welcome when trying to light a match. Again, hidden bonds and interactions are doing practical work everywhere. Then there are polymers, those long-chained molecules that give us rubber, plastic, many fabrics, and much else besides. A rubber band stretches because its molecular chains can be pulled into different configurations and then spring back. Plastic can be rigid or flexible depending on the details of its structure. Wool traps air and keeps warmth near the body because of how its fibres are shaped and arranged. Cotton absorbs water differently than synthetic fabrics. Wood has strength along the grain because of the alignment of its internal fibres and the biological architecture that formed as the tree grew. The ordinary world is a museum of bonding strategies, a quiet exhibition of how matter can be organised to produce wildly different behaviours from ingredients that are, at bottom, all part of the same physical universe. And this is before we even touch on taste, smell, colour, and texture, all of which also emerge from the properties of matter and the interactions between matter and light, or matter and the receptors in your body. The colour of a leaf, the transparency of glass, the smell of bread, the bitterness of coffee, the softness of velvet, the snap of cold celery. None of these are random decorations added after the fact. They are expressions of structure. They reveal how atoms are bonded, how electrons respond to light, how molecules fit into receptors, how surfaces are organised. The world around you is not only held together, it is characterised, enriched, and made legible by the specific ways in which it is held together. There is something quite comforting in realising that the everyday world is so deeply structured. A room is not just a collection of objects placed near one another. It is a gathering of stable arrangements that took shape because the laws of nature permit astonishing complexity. The ceramic of a mug, the foam in a cushion, the paint on a wall, the copper in a wire, the glass in a bulb, the wood in a bookshelf, each one is a success story of bonding. Different atoms, different arrangements, different scales of order, different ways of resisting both collapse and dispersal. Of course, these arrangements are not permanent. The hidden bonds in the world around you are strong enough to give form, but not so absolute that change becomes impossible. Wood rots, metal rusts, glass shatters, plastic degrades with enough light and time, fabrics fray, food spoils, molecules break and reform constantly. Even your own body is not a static sculpture, but a busy system of continuous repair, replacement and rearrangement. Matter holds together, then changes, then holds together differently. The world is stable enough for familiarity and dynamic enough for history. That may be one of the loveliest features of the ordinary world. It is dependable, but not frozen. A loaf bakes, ice melts, rain dries, iron tarnishes, paper yellows, fruit ripens. The hidden bonds of matter do not merely lock things in place. They make transformation possible in lawful and often useful ways. Cooking, building, growing, dissolving, freezing, healing, burning, fermenting. All of these are stories of bonds changing under new conditions. Chemistry is not just the reason things stay together. It is also the reason they can become something else. And yet, as rich as this everyday world is, it only answers part of our larger question. The hidden bonds around us explain why matter has texture, shape, strength, and character at the human scale. They explain why a stone can be a stone and a glass can be a glass rather than both being equally useless heaps. But if we widen the view again, another question starts to press forward. These earthly materials are all very well, but what gathers entire worlds? What keeps moons circling planets and planets circling stars? What shapes the enormous architecture above us, where objects are not held together by chemical bonds in any ordinary sense, but by something grander, slower, and more far-reaching? Because once the scale changes from tabletop to solar system, the universe begins relying on a different kind of loyalty altogether. That loyalty has a name, and it is probably the most familiar force in your life, even if it is also the one we most easily stop noticing. Gravity is so constant, so dependable, and so thoroughly woven into daily existence that it often fades into the background. It is the reason your feet stay on the floor instead of drifting toward the ceiling in a manner that would be inconvenient for furniture and very confusing for houseplants. It is the reason rain falls, rivers flow downhill, crumbs land in your lap instead of entering orbit, and the moon remains a companion rather than a former acquaintance. But gravity is not only a local downward pull, it is also the great gatherer of worlds. It is the reason matter can collect on enormous scales, the reason stars can form, the reason planets can exist, the reason galaxies hold together long enough to become grand, rotating cities of light instead of thin, anonymous fogs of scattered particles. One of the odd things about gravity is that it feels strong in the moment and weak in the wider physics of matter. You can feel it every time you lift a bag of groceries or stand up after a long day and notice that your legs have opinions about the matter. Yet compared with the forces that hold atoms and molecules together, gravity is extraordinarily feeble. A small refrigerator magnet can defeat the gravitational pull of the entire Earth on a paperclip, which is a quietly humbling fact if you are gravity, and somewhat encouraging if you are the magnet industry. At the level of tiny particles, gravity barely registers. It is not what gives a chair its shape. It is not what keeps a water molecule intact. It is not what makes a spoon a spoon. In the microscopic world, other interactions do the heavy lifting. And still, when we step back and consider the structure of the cosmos, gravity becomes the ruler of the large scale. That seems almost unfair at first. How can something so weak end up shaping the biggest things in existence? The answer lies in accumulation. Gravity has two important habits that make it unusually effective across great distances and great masses. First, it always attracts. There is no version of ordinary gravity that repels in the way electrical charges can either attract or repel depending on circumstance. Second, mass adds up. If you bring together enough material, each little bit contributes to the total pull. A single grain of dust exerts gravity, though not enough to impress anyone. A mountain exerts more, a planet more still, a star far more, a galaxy on a frankly excessive scale. Gravity wins the large-scale universe because it never cancels itself out in the simple way many other influences do, and because it is patient. It works slowly, steadily, and over enormous spans of time. It does not need drama. It only needs enough matter and enough time, and the universe has been generous with both. If you could take a vast cloud of gas drifting in space and simply leave it alone for long enough, gravity would begin its quiet work. Every bit of matter in the cloud would tug ever so slightly on every other bit. At first, the effect might be almost nothing, a faint tendency rather than an urgent event. But if some region of the cloud became even a little denser than the rest, it would pull in more material, becoming denser still, which would increase its pull further. Gravity favours growth by gathering. Small differences can become large outcomes. Over time, the cloud would begin to collapse inward in places, heating as it does, compressing, thickening, becoming something more structured than before. Given the right mass and conditions, a star could be born from this process. Around that star, leftover material might flatten into a disk, then clump, collide, and build planets. In that sense, gravity is not just a force that holds finished objects in place. It is a creative force in the most physical and practical sense. It helps make the objects in the first place. This is worth dwelling on because it changes how we think about the cosmos. Space is not filled with worlds as though someone carefully placed them there like ornaments. Worlds are consequences. They form because matter responds to gravity in predictable ways. A star is what can happen when enough gas collapses. A planet is what can happen when material orbits, collides, sticks, gathers, and clears a path around a star. A moon is what can happen when smaller bodies form around larger ones or are captured by them. The large architecture of the universe is not assembled by hand. It emerges because gravity gives scattered matter a reason to come together. Of course, If gravity merely pulled everything straight inward all the time, the universe would look very different. You would not get graceful orbits or long-lived systems, you would get a great deal of crashing. Useful in some contexts, perhaps, but not ideal for stable astronomy. The reason planets do not plunge directly into stars is that motion matters. A planet is not just sitting there waiting to be collected, it is moving sideways through space. Gravity bends that motion into a path. The result is orbit. It can be tempting to think of orbit as a kind of balancing act between falling and flying away, and while that image is not exact in every detail, it is close enough to be helpful. The planet is always being drawn inward by gravity, but it also has enough sideways motion that it keeps missing the star, so it falls around it rather than into it. This produces one of the loveliest features of the universe, which is that stability often comes from movement rather than stillness. The Earth is not held near the Sun by being fixed in place. It is held in a stable pattern by continuous motion shaped by gravity. The Moon is not hanging above us like a lamp suspended from an invisible ceiling. It too is in motion, constantly falling around the Earth. Stability here is dynamic. It is the kind of order that only exists because things keep moving in the right way. A solar system is not a frozen arrangement, it is a choreography. That choreography begins early in the life of a star system. When a young star forms from a collapsing cloud, not all of the material falls directly inward. Some of it has motion that causes it to settle into a rotating disk around the new star. Inside that disk, tiny particles collide. Some stick together. Little clumps become larger clumps. Large clumps begin attracting more material through gravity. There are setbacks, collisions, breakups, and general cosmic roughhousing. But over time, larger bodies emerge. In a sense, planets are what happens when gravity is given a messy workshop and a few million years to tidy things up. It is not a neat process. It is not polite, but it is remarkably productive. Once formed, planets continue to show what gravity can do. A planet that is large enough can hold an atmosphere because its gravity keeps gas from escaping too easily into space. A smaller world may struggle to do so, especially if it is warm or lacks protection from energetic particles streaming from a nearby star. Gravity also shapes a planet from the inside out. When enough matter gathers into one body, gravity pulls toward the center from all directions, encouraging the body to become round. This is why the large objects in space tend towards spheres or something close to them, while smaller objects can get away with being lumpy in the manner of badly stored potatoes. A mountain may rise on a planet, but a planet itself cannot keep the shape of a mountain forever. Gravity is simply too persistent. It wants balance around a center. This same inward pull can do more than make things round. It can squeeze interiors, create pressure, and produce heat. In the case of giant planets and stars, the consequences are profound. A star forms because gravity compresses matter so intensely that conditions in the core become extreme enough for new processes to begin, and those processes in turn produce the outward pressure that prevents total collapse for a very long time. Even after a star exists, gravity remains one half of its internal struggle. It is always there, always trying to gather the star more tightly. The star survives by answering back with pressure. In that sense, gravity is both creator and critic. It brings the star into being and then spends the rest of the star's life testing whether it can hold itself together against the pull that formed it. The same idea extends to galaxies. A galaxy is not merely a collection of stars that happen to be in the same neighbourhood. It is a gravitational system, a vast structure in which countless stars, clouds of gas, dust, and unseen matter all influence one another. Without gravity, a galaxy would not remain a galaxy for long. Its stars would simply continue on whatever paths they happen to have, and the whole graceful spiral or elliptical shape would unravel into dispersion. Instead, gravity gives a galaxy continuity. It keeps stars in motion around the galactic center, binds clusters, drives mergers and shapes the large-scale structure we observe in the universe. When galaxies interact or collide, it is gravity that choreographs the encounter, sometimes gently distorting them, sometimes dramatically rearranging them, always with the calm authority of a force that does not mind taking 100 million years to make its point. Tides offer a more intimate example of gravity acting across distance. The Moon does not only orbit the Earth, it also pulls on it. Because the Earth has size, the pull is not exactly the same at every point. This difference stretches the ocean slightly, helping create the tides. The Sun contributes too, and the combination of these effects gives us the regular rising and falling of sea levels that coastal life has always had to reckon with. Gravity here is not just keeping bodies in orbit, it is shaping daily experience, shorelines, marine ecosystems, and even the long history of life adapting to rhythmic change. The fact that the oceans move in response to distant masses is a fine reminder that gravity is not merely local. It links bodies across space in ways that can be gentle or dramatic depending on scale. Then there are the more extreme cases where gravity stops being the quiet manager of orderly systems and becomes something fierce. If a star much more massive than our Sun reaches the end of its life and can no longer support itself in the same way, gravity may win decisively. The star can collapse inward. Depending on the circumstances, the result may be a dense remnant such as a neutron star or something even stranger, a black hole. These are not places where gravity suddenly becomes a different force. They are places where the ordinary logic of mass gathering inward has been carried to extraordinary conclusions. A black hole is what happens when enough mass is compressed into a region so concentrated that the surrounding geometry of space and time becomes extreme. It is a reminder that gravity, patient though it is, can become overwhelming when matter is pushed far enough. This brings us to a deeper shift in understanding. For a long time, gravity was described as a force pulling masses toward one another, and that description works very well for many purposes. It lets us predict falling apples, planetary motion, and the paths of comets with remarkable success. But in the early 20th century, Albert Einstein offered a deeper picture. In his view, gravity is not quite a force in the old mechanical sense. Instead, mass and energy shape the geometry of space and time, and objects move through that curved geometry. This can sound abstract at first, but the key idea is practical. Matter tells space and time how to curve, and curved space and time tell matter how to move. If that sounds a bit like the universe has replaced invisible pulling with invisible bending, that is not entirely wrong. An everyday analogy can help, provided we do not lean on it too hard. Imagine a smooth surface altered by the presence of a heavy object so that the paths available across that surface are changed. Other objects moving nearby follow those altered paths. In the real universe, the situation is more subtle than a stretched sheet and does not happen in some outside space. Space and time themselves are part of the story. But the general point remains. What we experience as gravity is bound up with the shape of the arena in which motion happens. Planets orbit stars not because some mystical tether keeps reeling them in, but because the presence of the star changes the structure through which the planet moves. The path that would count as straight in such a curved setting is no longer what our ordinary intuition expects. This deeper picture matters because it explains things the older view could not fully capture. It helps explain why time itself runs differently in stronger gravitational environments. It predicts subtle shifts in planetary motion. It accounts for the bending of light by massive bodies, which means gravity can affect even things with no rest mass in the ordinary sense. Light passing near a massive object follows the curved geometry there, which can make distant objects appear distorted or multiplied. Astronomers use this effect to study galaxies and the distribution of matter in the cosmos. Once again, gravity is not merely holding worlds together. It is shaping what the universe looks like and how we are able to observe it. Still, for all the sophistication of relativity, It is also fine to preserve the older emotional truth that gravity gathers. It gathers dust into stones, stones into planets, gas into stars, stars into galaxies, galaxies into clusters. It gives the universe a tendency toward largeness with structure. Without gravity, matter might still interact in tiny local ways, but there would be no grand architecture, no stable planetary systems, no long slow collapse of clouds into suns, no galactic disks turning through darkness, no black holes at the hearts of large galaxies. Gravity is the reason the universe can build at scale. What makes this especially remarkable is that gravity works in a universe that is also expanding. On the very largest scales, space stretches and distant galaxies move away from one another. Yet locally and regionally, gravity can still overcome that general expansion where matter is dense enough. It can hold galaxies together. It can keep galaxy groups bound. It can preserve solar systems and planets and moons from being carried apart by the broader stretching of space. This is one reason the question of what holds the universe together has no single simple answer. Different effects dominate at different scales. The universe can be expanding overall, while still forming local islands of structure. Gravity is the great gatherer, but it gathers within a cosmos that is not globally standing still. There is also something almost philosophical about gravity's style. It does not shout. It does not need close contact. It does not concern itself only with the very small or the very immediate. It works across emptiness. It links bodies separated by enormous distances. It rewards accumulation and patience. If the stronger interactions of matter are like the detailed craftsmanship of the everyday world, then gravity is more like urban planning for the cosmos. It decides where the neighbourhoods of stars can form, where the traffic of orbits will flow, where the major structures can endure. And perhaps that is why gravity feels so fundamental to our imagination, as well as to physics. We grow up under it. We feel it in our muscles. We see its consequences in every falling object and every rising tide. Then, when we look upward, we discover it is also the same principle organising the heavens. The apple and the moon belong to the same story. The stone in your hand and the star above your roof are not governed by unrelated ideas. They are participants in one great continuity, one set of rules connecting the household and the cosmic. Physics is often at its most satisfying when it reveals that very large things and very ordinary things are expressions of the same underlying order. Yet for all gravity's reach, it does not explain everything about what holds reality together. Gravity gathers worlds, yes. It builds stars and shapes galaxies and keeps moons loyal. But it does not tell us why matter is solid to the touch, why atoms keep their electrons, why light and chemistry rule so much of the visible world, why magnets cling to refrigerators with such unearned confidence, or why your hair occasionally behaves as though static electricity has become a personal philosophy. For that, we have to turn from the great architecture of the cosmos to another influence, one that dominates the scale of ordinary matter and helps give the everyday world its structure, colour, light and texture. That influence is electromagnetism, and if gravity is the quiet architect of worlds, electromagnetism is the reason those worlds have texture, colour, chemistry, light, and most of the ordinary detail by which we recognise them. Gravity may gather a planet into a sphere and keep it loyal to its star, but electromagnetism decides whether that planet has rocks, oceans, clouds, lightning, metal, glass, salt, skin, paper, and tea kettles that can very much burn your hand if approached carelessly. It is not an exaggeration to say that much of everyday reality is really a long performance of electromagnetic behaviour. The shape of matter around you, the reason it resists your touch, the reason you can see it at all, the reason atoms link into molecules and molecules into the familiar world, all of that belongs largely to this one great interaction. This can seem odd at first because electromagnetism sounds technical in a way gravity does not. Gravity feels like common property. Everybody has dropped something. everybody has felt weight. Electromagnetism sounds like it belongs to laboratories, wires, and old science classrooms with slightly overworked demonstration equipment. But in truth, you're in contact with the electromagnetism almost constantly, and far more intimately than you are with gravity in most of your daily perceptions. When you sit in a chair, the chair does not really hold you up by gravity. Gravity is pulling you downward, certainly, but what stops you from passing through the chair is electromagnetic interaction between the atoms in your body and the atoms in the chair. When you look at the room around you, the light entering your eyes is electromagnetic radiation. When you feel warmth from the sun or a radiator, that too is electromagnetic energy. When your phone works, when a magnet clings to a fridge, when static makes a sleeve cling to your arm, when chemistry gives you breath and blood and memory, electromagnetism is there in one form or another. One way to begin understanding its importance is to remember that atoms are made of charged components. There are positively charged particles in the nucleus and negatively charged electrons surrounding that nucleus in structured ways. Charge is one of the great organizing principles of matter. Opposite charges attract, like charges repel. From that basic fact unfolds an enormous fraction of the world we know. If gravity gathers matter simply because mass attracts mass, electromagnetism is more nuanced and more locally powerful. It can pull things together, push them apart, sort them into patterns, and determine how particles arrange themselves with astonishing precision. This is why electromagnetism dominates the scale of ordinary material life. At the level of atoms and molecules, electrical forces between charged particles are vastly stronger than gravity. Gravity still exists there, quietly making no fuss, but it is not the main event. It is like bringing a polite candle to compete with a lighthouse. The reason electrons stay associated with nuclei, the reason atoms form structured electron arrangements, the reason those atoms can then bond into molecules, all of this depends on electromagnetic attraction and the quantum rules that shape how charged particles may exist together. That second part matters. Electromagnetism does not work alone in some simplistic mechanical sense. It operates in a world governed by the rules of quantum behavior, which means electrons do not orbit nuclei like tiny planets in the old textbook picture. They occupy allowed states, structured possibilities, regions where they can be found with certain probabilities. This sounds more complicated than one might want in the middle of a calm evening, but the important point is simple enough. The shape and stability of atoms come from electromagnetic attraction, guided by quantum rules. Without that combination, there would be no ordinary chemistry and therefore no familiar world to speak of. Think of hydrogen, the simplest atom, a single positively charged proton with a single electron associated with it. From that humble beginning, nature can build upward through combinations and transformations into the rich periodic variety of elements. Each element has its own characteristic number of protons in the nucleus, and that number determines how many electrons it can have when neutral. Those electrons arrange themselves in ways that give each element its habits and preferences. Some are eager to share electrons, some prefer to gain them, some are inclined to give them away, some are largely indifferent and behave with the social reserve of guests who intend to leave early. The chemistry of the universe arises from these patterns. Matter has personality, if one may use the term loosely, because of electromagnetism and electron arrangement. This is why the periodic table is not just a filing cabinet for atoms, it is a map of how matter is likely to behave. Carbon can build elaborate structures because of the way its electrons allow it to bond. Oxygen is highly reactive in certain contexts because of what its electron arrangement makes favourable. Sodium and chlorine combine readily to form salt because what is unstable separately can become stable together through an exchange of electrons and the resulting electrical attraction. Water forms because oxygen and hydrogen can share electrons in a particular way. Proteins fold, sugars dissolve, metals conduct, ceramics resist heat, and glass remains transparent largely because electromagnetism, guided by atomic structure, allows those outcomes. It is difficult to overstate how much of everyday reality depends on atoms finding preferred electromagnetic arrangements. The floor beneath you is not solid because its atoms are jammed together like pebbles in cement with no room to breathe. It is solid because the electrons associated with those atoms occupy states that create a stable structure and resist compression in very specific ways. Push against a wall, and what you feel is not the hard touch of tiny nuclei stacked against one another. You are feeling the electromagnetic refusal of matter to let your atoms settle into the same states as the wall's atoms. It is a denial delivered with absolute consistency and considerable practical importance. That sense of solidity is one of the most convincing features of the material world, and yet it is not elementary in the way our senses suggest. It emerges from charged particles, quantum rules, and organized electron behavior. This is one reason physics can feel so delightfully at odds with instinct. The table seems solid because that is what solidity feels like to a creature our size. But at the deeper level, the table is a stable arrangement of atoms whose electrons and nuclei behave according to rules that do not resemble woodwork in any obvious way. Ordinary life is built on invisible sophistication. Light itself also belongs to electromagnetism. And here the story becomes even more immediate because vision is one of the main ways we inhabit the world. The sunlight that crosses a room, the glow of a lamp, the blue of the evening sky, the green of leaves, the colour of your blanket or curtains or mug, all of it depends on how electromagnetic radiation is emitted, transmitted, absorbed, and reflected. Light is not a separate bonus feature added onto matter after the universe finished with the important work. It is woven into the same interaction that shapes atoms and molecules. The world is visible because electromagnetism governs both matter and radiation in a deeply unified way. When light strikes a surface, the electrons in that material respond. Some wavelengths may be absorbed, others reflected or scattered. The details depend on the structure of the material and the allowed energy changes of its electrons. A red apple appears red because its surface is handling incoming light in a way that sends red wavelengths outward to your eyes more readily than others. A clear window remains transparent because its material does not strongly absorb visible light in the same way many opaque substances do. A shiny metal surface reflects strongly because of how its electrons respond collectively to incoming electromagnetic waves. Colour, shine, dullness, translucence, and darkness are not superficial decorations. They are clues to electromagnetic behaviour. The sky itself offers a fine example. Sunlight arrives containing many wavelengths. As that light passes through the atmosphere, shorter wavelengths are scattered more effectively by the molecules in the air, which is why the sky appears blue by day. At sunset, the light has travelled through more atmosphere, and much of the shorter wavelength light has been scattered away from the direct path, leaving the longer reds and oranges more prominent. It is one of the most ordinary beautiful sights on Earth, and it is also a demonstration of electromagnetism in action on a planetary scale. The world is not merely illuminated by electromagnetic radiation, it is painted by it. Warmth, too, often arrives electromagnetically. The heat you feel from sunlight is energy carried across space by radiation. You do not need hot air from the sun blowing onto your face, which is fortunate because the logistics would be distressing. Instead, electromagnetic waves travel through the vacuum of space and deliver energy when absorbed by matter. Your skin warms, stone warms, roofs warm, oceans warm. Climate itself depends on this exchange. The balance between incoming solar radiation and outgoing thermal radiation is one of the central facts of planetary life. Even here, where the topic begins to sound large again, electromagnetism remains the main language of the process. Then there is electricity in the more familiar sense, the controlled motion of charged particles through materials. In metals, certain electrons can move relatively freely through the structure, which is why metals are so good at conducting electrical current. This simple fact has transformed human civilization to such an extent that it is easy to forget how extraordinary it is. Our homes, devices, communications, and much of modern industry rely on the ability of materials to carry charge in predictable ways. A switch, a bulb, a wire, a battery, a motor, a charger, a speaker, all are practical uses of electromagnetic principles. When you charge a phone beside your bed and then use it to check the weather or message a friend or ignore your sleep schedule, you are depending on charged particles behaving in the ways electromagnetism allows. Magnetism, once thought of as a rather separate curiosity, is deeply linked to electricity. Moving charges create magnetic effects. Changing magnetic conditions can induce electrical currents. The modern understanding of electromagnetism united these into one framework, which is one of the great intellectual achievements in the history of physics. A magnet clinging to a refrigerator door is not performing a household miracle by itself. Its behavior is connected to the structure and motion of charges within materials. The refrigerator, to its credit, participates with admirable restraint. Magnetic fields are another face of the same broad interaction. They can guide charged particles, store energy, influence materials, and make possible everything from electric motors to magnetic resonance imaging. It is remarkable how often this interaction can feel both subtle and forceful. Static electricity is a fine example. Shuffle across a carpet in dry air and then touch a metal handle, and suddenly the universe offers a small but pointed lesson about charge imbalance. Electrons have been redistributed. A difference in electrical condition has built up. The spark is a rapid correction. It is a trivial event by cosmic standards, but it makes the invisible feel personal very quickly. Hair lifting, fabric clinging, balloons sticking to walls, all are little domestic reminders that charge matters. In living systems, electromagnetism is everywhere. Nerve signals depend on electrical differences across cell membranes. Muscles contract through electrically governed processes. The chemistry of metabolism, the folding of proteins, the copying of genetic material, the transport of ions, the binding of molecules to receptors, all are electromagnetic stories. Life is not separate from physics. It is one of the most elaborate consequences of it. The difference between a stone and a living cell is not that one has physics and the other escapes it. The difference is that in living systems, electromagnetic interactions are organized into extremely sophisticated networks capable of self-maintenance, response, and reproduction. The hidden bonds we spoke of earlier become, in biology, part of a far richer pattern. Your own senses are electromagnetic in startlingly direct ways. Vision depends on light interacting with molecules in the eye. Touch depends on the electromagnetic resistance of matter and the nervous system's interpretation of mechanical pressure. Taste and smell depend on molecules interacting with receptors whose shape and charge properties determine what binds and what signal follows. Hearing begins with mechanical vibrations. Yes, but the conversion of those vibrations into nerve impulses again depends on charged particles and cellular electrical behavior. Much of your experience of reality is therefore shaped by how electromagnetism operates both outside and inside your body. We are not merely surrounded by an electromagnetic world. We are built to perceive it. This begins to explain why everyday reality feels so rich. Gravity gives us large-scale order, but electromagnetism gives us difference. It distinguishes one material from another. It makes matter rigid here, flexible there, reflective in one place and absorbent in another. It gives chemistry its range and thereby gives the world its variety. Without electromagnetism, there would be no ordinary matter in the sense we know it. There might still be mass, perhaps, and gravity could still gather it on large scales, but there would be no atoms with familiar electron structure, no molecules, no liquid water, no solid wood, no atmosphere behaving in familiar ways, no biology, no light interacting with eyes. The universe would be almost unrecognizable. Even the distinction between what is soft and what is hard, what is brittle and what is springy, what melts easily and what stands firm in heat, comes down to electromagnetic arrangements. In some materials, atoms are locked into rigid repeating networks. In others, layers can slide. In still others, long molecular chains can bend and recoil. A ceramic mug, a steel spoon, a cotton sheet, a rubber band, and a block of ice are all built from atoms and all obey the same fundamental laws. But the details of their electromagnetic structure differ enough to produce very different realities at the scale of hands and rooms and kitchens. Physics does not give us monotony. It gives us a deep reason why variety is possible. There is a modest kind of wonder in that. You do not need to leave the house, build a telescope, or contemplate black holes to meet the profound. It is already present in the simplest objects. A glass of water on a table is a triumph of electromagnetic order. So is a page of a book, a strand of hair, a candle flame, a loaf of bread, a ceramic tile, the glow of a screen in a dark room. Everyday life is dense with successful negotiations between charge, structure, energy, and motion. Ordinary objects are not boring once you remember what they're doing, and yet electromagnetism, for all its reach, still does not answer the whole question of what holds reality together. It explains the visible world around us with extraordinary success. It gives us atoms, chemistry, light, electricity, and most of the practical business of material life. But it does not explain why the positively charged components deep inside atomic nuclei do not simply repel one another and fly apart. If you take the logic of charge seriously, that becomes a pressing question. A nucleus is crowded with particles, some of them carrying the same positive charge. Electromagnetically speaking, that arrangement ought to be rather difficult to maintain, and yet nuclei do exist. Matter exists. The hearts of atoms stay intact, which means that, hidden deeper still, another interaction has been doing an even more demanding job all along. If electromagnetism gives the everyday world its texture, colour, chemistry, and solidity, then the next question arrives almost automatically once we peer into the atom itself. Why does the nucleus stay together? Why does the heart of the atom not simply tear itself apart the moment it forms? After all, the nucleus contains protons, and protons carry positive electric charge. We've already seen that like charges repel. That is one of the first great habits of electromagnetism. Bring two positively charged objects together, and they do not behave like old friends. They push away from one another, so the atomic nucleus presents us with a problem that is both simple and deeply important. How can a tiny, crowded bundle of positively charged particles remain bound at all? This is one of those places where the universe seems to answer a very sensible question with a slightly outrageous idea. The reason the nucleus stays together is that there is another interaction at work, one stronger than the electromagnetic repulsion between protons, but effective only over very short distances. This is the strong force, or more carefully, the strong interaction. It is one of the deepest reasons matter can exist in the form we know. Without it, there would be no stable atomic nuclei beyond the simplest possible cases, no rich variety of elements, no stars forging heavier matter, no planets made of iron and oxygen and silicon, no calcium in bones, no carbon-based life, no familiar universe of material complexity. The strong interaction does not merely tidy up a technical difficulty inside the atom, it makes the world possible. One way to appreciate its importance is to imagine the nucleus without it. A nucleus is incredibly small, far smaller than the overall size of the atom. Nearly all the mass of the atom is concentrated there, packed into a region so tiny that ordinary intuition becomes useless almost immediately. Protons sit together in this confined space. close enough that their mutual electrical repulsion is not some negligible side issue. It is intense. If electromagnetism were the only relevant influence there, the protons would not remain crowded together. They would push apart. The nucleus would fail to hold. The atom, as a durable structure with a dense centre and surrounding electrons, would not exist in any recognizable way. Matter would be gutted at its core, and yet nuclei do exist. Hydrogen has the simplest one, just a single proton in the common form. Helium has 2 protons and usually 2 neutrons. Carbon has 6 protons and commonly 6 neutrons. Oxygen has 8 and 8. Iron, gold, uranium, all the heavier elements you could name or use to intimidate a chemistry student, contain many protons crowded together. The fact that these nuclei can survive tells us immediately that some binding influence must be overcoming the electrical repulsion, at least at close range. The strong interaction is that influence, and the more one learns about it, the stranger and more impressive it becomes. At first glance, one might imagine the strong force as a kind of tiny glue, a microscopic adhesive smeared between protons and neutrons in the nucleus, quietly holding them in a compact cluster. That image is not entirely useless, but it is much too simple. The strong interaction is not like paste or string or bolts fastening particles into place. It belongs to the quantum world, where particles are not hard little beads, and forces are not quite the same sort of pushes and pulls we picture in everyday mechanics. The deeper story begins even below the level of protons and neutrons themselves, because protons and neutrons are not fundamental particles in the way people once imagined. They are made of smaller constituents called quarks. This is where the atom begins to reveal that its heart is not a tiny billiard ball, but a layered structure. A proton is built from quarks. A neutron is built from quarks as well. These quarks are held together by the deeper form of the strong interaction, and the carriers associated with that interaction are called gluons, a wonderfully honest name as particle physics goes. There is something almost refreshing about it. They are called gluons because they help do the binding, but of course this is the universe, so even the glue is not simple. Gluons do not merely sit there passively holding quarks in place. They are part of a restless dynamic quantum system. The strong interaction is alive with exchange and structure. The inside of a proton is not still. It is a busy place. This deeper level matters because what we usually call the strong force inside the nucleus is really a kind of leftover effect, a residual consequence of the more fundamental strong interaction that binds quarks into protons and neutrons in the first place. There is a useful everyday analogy here, provided we treat it gently. Imagine molecules that are electrically neutral overall but still capable of attracting each other because of how charge is distributed within them. Something similar happens here in spirit, though the actual physics is much more exotic. Protons and neutrons are each composite objects built from quarks, and the strong interaction that binds those quarks leaves behind a residual power capable of binding protons and neutrons to one another when they come very close. In other words, the nucleus is held together not by the deepest strong interaction directly in its simplest form, but by its lingering influence between these larger composite particles. That lingering influence is astonishingly powerful at short distances. This is the key. The strong interaction does not reach out across the room like gravity, nor does it stretch across ordinary scales like electromagnetism can. It is intensely local. Within the tiny confines of the nucleus, it can overcome proton repulsion and create a stable bound system. But step too far away, even by subatomic standards, and its effectiveness drops off rapidly. It is like the most committed host imaginable, deeply attentive to the guests once they are inside the house, but entirely uninterested in collecting anyone from the next town over. Gravity is long-ranged and patient. Electromagnetism is strong and versatile. The strong interaction is ferocious but short-armed. This short range explains a great deal about nuclei. Small nuclei can be very stable, because the strong binding between nearby particles is enough to hold everything together comfortably. But as nuclei get larger and larger, the balance becomes trickier. Each added proton increases the electrical repulsion in the nucleus, because every proton repels every other proton. The strong interaction does not simply scale up with the same generosity across the whole nucleus, because it works most effectively over very short separations between neighbouring particles. This means that very heavy nuclei face a mounting internal tension. The protons are numerous, their repulsion accumulates, and the short-range binding has to work harder and harder to maintain order. That is why the heaviest nuclei can become unstable. The strong interaction is magnificent, but even it has limits within crowded nuclear architecture. Neutrons play an important role in this story. A neutron has no electric charge overall, which means it does not add to the proton-proton repulsion problem. But it does participate in the strong interaction, so neutrons can contribute binding without increasing electrical pushback. In a sense, they are the diplomatic staff of the nucleus, helping maintain cohesion in a room where too many positively charged personalities might otherwise make cooperation impossible. This is one reason heavier nuclei generally need more neutrons than protons to remain stable. The larger the nucleus becomes, the more neutrons are needed to help offset the growing electric strain. Even so, beyond a certain point, no amount of diplomatic skill can keep the gathering indefinitely peaceful. The heaviest nuclei remain vulnerable to change. All of this may sound very remote, but it has consequences that ripple outward through the entire history of the universe. In the early universe, after the first moments of extreme heat and density, conditions cooled enough for the simplest nuclei to form. Hydrogen and helium emerged in abundance, along with a little bit of lithium. Much heavier elements did not appear in large amounts then. For those, the universe needed stars. Inside stars, gravity compresses matter so intensely that nuclei can be pushed close enough together for the strong interaction to take over and bind them into new, heavier nuclei. This process is what we call nuclear fusion. It is one of the central creative acts of the cosmos. Fusion works because under the right conditions, the strong interaction rewards closeness. But getting positively charged nuclei close enough is not easy, because electromagnetism resists the approach. This means stars need enormous temperatures and pressures to make it happen. The nuclei must move with great energy, collide, and sometimes overcome their mutual electrical repulsion, enough for the short-range strong interaction to seize the opportunity. Once that happens, a new nucleus can form, often with energy released in the process. That energy helps support the star against gravitational collapse and provides the light and heat stars pour into surrounding space. So when you feel sunlight on your skin, or watch dawn brighten a room, you're in a very real sense benefiting from the strong interaction at work in the core of a star. The atom's heart and the warmth of morning are not separate stories. The strong interaction is also the reason the elements themselves can exist as more than a sparse collection of hydrogen. Carbon, oxygen, neon, silicon, iron all owe their existence to nuclear processes in stars and stellar explosions, and those processes depend entirely on nuclei being able to hold together when formed. The calcium in your bones, the phosphorus in your cells, the iron once moving through blood, the oxygen you breathe and the carbon structure of living chemistry all pass through this nuclear history. They were forged because the strong interaction makes nuclei possible, allows them to bind, and under the right circumstances permits one nucleus to become another. Matter is not merely assembled once and left unchanged. It is transmuted over cosmic time through processes made possible by nuclear binding. There is another subtle marvel here. Most of the mass of ordinary matter does not come simply from the masses of the quarks inside protons and neutrons, taken by themselves in a naive way. A great deal of the mass we experience in everyday matter is associated with the energy of the strong interaction within these particles. In other words, much of what makes matter substantial, what gives the world weight and heft, is tied to this busy internal life of quarks and gluons. A proton is not just a bag holding 3 quarks with a little empty room to spare. Its mass reflects an energetic quantum system bound by the strong interaction. That means the strong interaction is not only keeping nuclei together, it is also deeply involved in what makes the material world materially present at all. This is one of those facts that can quietly rearrange the way one sees everyday things. A stone feels heavy. A loaf of bread has heft. Your own body presses into a mattress or chair. We tend to think of mass as a straightforward property, something that just belongs to stuff in the same way redness belongs to strawberries, or dampness belongs to rain. But at the deepest level, the substance of matter is bound up with hidden energies and interactions. The strong interaction is part of the reason the world is not ghostly. It helps make matter matter. Of course, the strong interaction does not act indiscriminately. Not every possible nucleus is stable. Not every arrangement of protons and neutrons can endure. Some combinations last practically forever on human timescales. Others survive only briefly before changing. This gives nuclear physics a landscape of stability and instability, of favoured configurations and awkward compromises. Certain numbers of protons and neutrons produce especially stable nuclei. Others result in nuclei that are prone to decay, splitting or transforming through other interactions. This is important because it reminds us that holding together in nature is rarely absolute. The strong interaction can create binding, but the resulting structure still depends on the detailed balance of all the ingredients involved. There is also a tendency, when speaking of the strong force, to imagine it as somehow simple because it is powerful. But in truth, it is one of the more mathematically intricate parts of modern physics. The rules governing quarks and gluons are subtle, and one of their striking features is that quarks are not found isolated in ordinary conditions. They are confined. Try to pull them apart and the interaction does not weaken in the simple way one might expect. Instead, the system resists separation so strongly that new particles can emerge before lone quarks ever appear. This is very unlike gravity or electromagnetism, where one can easily observe isolated masses or charges. Quarks remain bound inside composite particles. The strong interaction is not just strong, it is possessive. That possessiveness has an almost comic contrast with the residual strong interaction in nuclei, which is strong enough to hold protons and neutrons together, but not so dominant that nuclei become limitless towers of bound particles. Again, the universe prefers balance over caricature. Too weak, and nothing substantial forms. Too strong in the wrong way, and complexity might be impossible. What exists instead is an interaction of extraordinary strength, operating with extraordinary specificity. It builds the atom's heart without turning all matter into one universal lump. Nuclear energy, both in stars and in human technology, is one of the most dramatic visible consequences of this hidden binding. When nuclei fuse or split, the changes in binding can release immense amounts of energy compared with ordinary chemical reactions. Burning wood, digesting food, and charging batteries all involve electromagnetic rearrangements of electrons and atoms. Powerful as those processes are for ordinary life, they are modest beside nuclear changes. This is because nuclear binding reaches into a much deeper layer of matter. Rearranging the atom's heart taps a more concentrated reserve. It is one reason stars shine for so long, and also one reason nuclear technologies demand such care. This strong interaction is generous with energy when nuclear structures change, and nature does not distribute that generosity without consequences. Still, there is something quietly elegant about the role this interaction plays. It solves a problem created by the very existence of charged particles in close quarters. It allows protons and neutrons to become durable nuclei. It makes the elements possible. It underwrites stellar fusion, and therefore starlight. It contributes to the mass of matter. It turns a universe that might have consisted mostly of simple particles into one capable of chemistry, geology, biology, and listeners who can grow sleepy while thinking about quarks. The atom's heart holds because the universe contains a force willing to do a difficult job very close up and with tremendous efficiency. And yet even here, at the centre of matter, stability is not the whole story. Some nuclei are secure, others are uneasy. Some can persist for ages while others seem almost to hesitate before changing into something else. There is a quiet restlessness hidden inside certain atoms, a tendency toward transformation that the strong interaction alone does not prevent. When that restlessness becomes important, another interaction enters the scene, subtler than electromagnetism, far weaker in direct strength than the strong interaction, yet absolutely essential to how the universe evolves. Because the atom's heart may hold, but sometimes it also changes, and when it does, the next part of the story begins there. If the strong interaction is what allows the atom to have a heart at all, then the next part of the story begins with a quieter and stranger fact. Not every heart remains exactly as it is. Some nuclei are stable in a way that seems almost serene. They can sit unchanged for spans of time so long that from a human point of view they might as well be eternal. Others are less settled. They contain an imbalance, a tension, a kind of internal awkwardness that does not always announce itself dramatically, but eventually resolves. A particle changes identity. A nucleus shifts its composition. Something that was one element becomes another. And this happens not because the strong interaction suddenly forgets its job, nor because electromagnetism barges in and tears the place apart, but because another interaction is involved. Much quieter in daily life, much less obvious than gravity or light or chemistry, and yet absolutely essential to the unfolding of the universe. This is the weak interaction, often called the weak force, though the word weak can be misleading if it tempts us to think unimportant. It is subtle, yes. It is elusive. It does not dominate the world of touch and colour the way electromagnetism does, nor does it gather stars and planets the way gravity does, nor bind quarks with the ferocity of the strong interaction. But without it, the universe would be a very different and much poorer place. There is something fitting about that. The weak interaction operates almost like a hidden editor in the story of matter. It does not build the major structures by brute force. It does not usually announce itself in the obvious architecture of things. What it does instead is allow certain forms of change that would otherwise not occur. It permits transformation at the level of particles. It lets one type of constituent become another under the right conditions. It is involved in radioactivity, in stellar processes, in the creation of neutrinos, in the balance between protons and neutrons, and therefore in the very possibility of a rich universe full of elements and long-lived stars. If the strong interaction holds matter together at the deepest close range, the weak interaction is one of the great reasons matter is not frozen forever into its first and simplest forms. To understand why this matters, it helps to begin with a familiar but still remarkable fact. Some atoms are radioactive. That word can sound dramatic because we tend to associate it with glowing warnings, historical accidents, or the sort of villains who seem suspiciously overcommitted to green lighting. But radioactivity, at its core, is simply the spontaneous transformation of unstable atomic nuclei. Certain nuclei are not comfortable remaining what they are. Given time, they change. Sometimes they emit a helium nucleus, sometimes they split. And sometimes, in one of the most important cases for our story, a neutron inside the nucleus turns into a proton, or under certain conditions a proton turns into a neutron. This sort of change is governed by the weak interaction. That sentence may not sound immediately thrilling, but it carries enormous consequences. A neutron and a proton are close relatives in many ways. They are both heavy constituents of the nucleus. They are both made of quarks, yet they differ in electric charge, and that difference changes everything about how an atom behaves. If the number of protons in the nucleus changes, the identity of the element changes. Add or remove a proton, and you're no longer dealing with the same element at all. Hydrogen becomes helium, carbon becomes nitrogen, one chemical personality becomes another. The weak interaction is what allows that shift at the particle level. It gives the universe a way to rewrite matter from within. Consider a free neutron, one not safely tucked inside a stable nucleus. Left on its own, it does not last forever. After a while it decays. It turns into a proton, an electron, and a neutrino. That is an astonishing thing when you stop to think about it. A particle simply changes character. The universe permits it to do so because the weak interaction exists. One of the quarks inside the neutron changes type, and the result is a proton instead. The electron and neutrino carry away the necessary balance of energy and other properties. It is not the kind of process our everyday intuition prepares us for. A wooden chair does not quietly become a violin and a moth. Yet at the level of fundamental particles, identity can shift. Matter is less fixed than it appears. This process, often known as beta decay in one of its forms, is one of the classic signatures of the weak interaction. A neutron-rich nucleus can use this route to become more stable. One of its neutrons becomes a proton, and the nucleus climbs upward by one place in the periodic order of elements. A different substance emerges from within the old one. The atom has not been smashed from outside. It has revised itself internally. The weak interaction is the mechanism of that revision. There is something almost philosophical about this. Much of our discussion so far has been about what holds things together. Here, for the first time in a deep way, we begin to focus on what allows things to change without ceasing to be part of a lawful universe. The weak interaction is not simply an agent of destruction. It is an agent of rebalancing. It allows unstable arrangements to find more stable ones. It permits the universe to move from one form of matter to another. In that sense, its subtle unravelling is also a kind of quiet correction. A nucleus that cannot remain as it is does not simply fall into nonsense. It transforms according to rules. This role becomes even more profound when we leave radioactive rocks and laboratory instruments behind and look at the stars. Because the weak interaction is not only involved in certain decays on Earth, it is also central to the process by which stars like the Sun shine. That may seem surprising. One tends to imagine starlight as the domain of gravity and the strong interaction, and certainly both are essential. Gravity compresses the star. The strong interaction is what ultimately binds nuclei together during fusion. But the weak interaction plays a crucial part in getting the process started in stars like our own. Inside the Sun, the main business of energy production begins with hydrogen. Hydrogen nuclei, which are single protons in their common form, must somehow be turned into helium if the star is to tap the energy released by fusion. But there is a problem. A helium nucleus contains 2 protons and 2 neutrons. Starting from protons alone, something must allow some of those protons to become neutrons. That is where the weak interaction enters the story. In one of the earlier steps of the chain that powers the Sun, 2 protons come very close, and through a process involving the weak interaction, one of them is transformed into a neutron. This makes it possible for a bound deuterium nucleus to form, containing 1 proton and 1 neutron. From there, the path toward helium continues. Without this step, ordinary hydrogen burning in stars like the Sun would not proceed in the same way. The Sun would not shine as it does. Our familiar star, with its long steady output over billions of years, depends in part on the weak interaction being what it is. This is especially interesting because the weak interaction does its job rather slowly by nuclear standards. If it were much stronger, stars like the Sun might race through their fuel more rapidly. If it were absent or far weaker in the wrong way, the stellar story would be radically altered. The quiet pace of solar life, so important for the long development of planets and biology, owes something to the fact that the weak interaction is subtle rather than flamboyant. That slowness is one of its defining features. The weak interaction governs processes that can take place rarely, or with small probabilities compared with what the strong interaction can achieve once conditions are right. This is part of why radioactive decay can be unpredictable for any single nucleus, while still obeying precise statistical laws for large collections. One unstable atom might decay now, another much later. There is no ticking countdown visible inside each one, and yet, taken together, vast numbers of them reveal steady patterns, characteristic times, reliable rates. The weak interaction gives nature a strange combination of spontaneity and order. At the level of the individual event, there is unpredictability. At the level of the ensemble, there is law. This is not only important for nuclear physics, it is also one of the reasons the universe can have history. If every transformation happened immediately, much of the richness of time would disappear. If nothing transformed at all, the universe would remain trapped in a simpler state. The weak interaction allows delayed change. It builds patience into matter. Certain nuclei linger, then transform. Certain stellar steps proceed slowly enough to sustain long-burning lives. Certain cosmic processes unfold over ages rather than moments. The universe is not merely held together, it is paced. There is another character in this story, one so elusive that for a long time it seemed almost beyond belief, the neutrino. When certain weak interaction processes occur, neutrinos are produced. These are extraordinarily light, electrically neutral particles that interact so feebly with matter that vast numbers of them pass through your body every second without the slightest fuss. Neutrinos from the sun stream through the Earth continuously. They pass through rock, air, ocean, and flesh with almost no interruption. They are among the most ghost-like inhabitants of reality, though ghost-like in the most lawful and physical sense. The existence of neutrinos was first proposed because something seemed missing in certain radioactive decays. Energy and momentum appeared not to balance properly if only the obvious particles were counted. Rather than abandon the idea that nature keeps good accounts, physicists proposed that another particle must be escaping detection and carrying away the missing share. That particle was the neutrino. Later it was detected, and its behaviour has become one of the great subtle stories of modern physics. The weak interaction is the main way neutrinos participate in the world. Without it, they would hardly matter at all. With it, they become clues to stellar interiors, supernova, nuclear reactions, and some of the deepest puzzles in particle physics. There is something almost poetic, in a very restrained scientific sense, about the fact that stars announce their inner workings not only through light, but also through floods of particles that scarcely stop for anything. Neutrinos from the sun reach us directly from the nuclear processes deep inside it, carrying information from regions light cannot leave immediately. Light from the sun's core takes a very long wandering path to the surface before escaping. Neutrinos depart with far less delay. In that sense, the weak interaction gives the cosmos one of its quietest messengers. The weak interaction also played a major role in the early universe, when temperatures were extreme and particles transformed readily. In those first moments, the balance between protons and neutrons was not fixed forever. Weak interaction processes helped determine how many of each would remain as the universe cooled. That balance in turn influenced what nuclei could form when the first light elements were assembled. If the weak interaction had behaved differently, the early composition of the universe might have changed in ways that would echo all the way forward into star formation, chemistry, and life. So when we say the weak interaction matters, we do not simply mean it appears occasionally in a radioactive laboratory source or a faint detector buried underground. We mean it helped set the opening conditions for the material cosmos. It is also worth noting that the weak interaction is unusual in another way. It does not treat all symmetries with the same politeness one might expect from other interactions. In the history of physics, one of the great surprises of the 20th century was the discovery that the weak interaction distinguishes between certain mirror-related possibilities. In simple terms, nature turned out not to be perfectly indifferent to left and right in this domain. That was a profound shock, because symmetry had seemed so natural and so reliable elsewhere. The weak interaction, with calm audacity, violated that expectation. The universe, it turns out, is not obligated to preserve every neat idea we invent about fairness and balance. Sometimes the laws have preferences, subtle ones, but real. This may sound like a very abstract point, but it matters because it reminds us that the weak interaction is not merely a fainter copy of something else. It has its own character. It is short-ranged. It acts in specific kinds of particle transformation. It involves heavy carrier particles, which is one reason its range is so limited. It produces neutrinos and participates in processes that change the flavour, if one may use the technical term, of quarks and leptons. It is part of the reason the particle world is not static. The weak interaction gives matter ways to become other matter, and once you begin to think in those terms, a great many natural processes come into better focus. Radioactive dating, for example, depends on the steady transformation of unstable nuclei over time. Certain isotopes decay at known statistical rates, allowing us to estimate the ages of rocks, fossils, and archaeological remains. In other words, the weak interaction helps us tell time in the history of Earth and life. It is one of the reasons geology can speak in ages, and biology can trace lineages through deep time. That is a strikingly large cultural consequence for an interaction that most people never think about while making breakfast. The weak interaction also helps shape what can happen in the aftermath of stellar death. In supernova explosions and other extreme environments, weak processes influence how matter behaves under astonishing conditions. Neutrinos can carry away huge amounts of energy. Particle transformations can alter the composition of matter in dense stellar remnants. The creation of some of the heavier elements in violent cosmic events depends on chains of nuclear reactions and decays in which the weak interaction is indispensable. So even the gold in a ring, or the iodine in the body, or the rare heavy atoms in old rocks may owe something to these quiet transformative rules playing out in catastrophic places. What is so fascinating here is that the weak interaction gives the universe a controlled way to come undone and be remade. The phrase unravelling can sound purely negative, as though it implies only loss. But subtle unravelling is often what allows further structure. A neutron becomes a proton, and now a different nucleus can exist. A radioactive atom decays and becomes another element. A stellar fusion chain proceeds because a proton can change identity. Heavy unstable nuclei transform through sequences that create new species of matter. The weak interaction is not the enemy of order. It is one of the reasons order can evolve. There is perhaps a broader lesson hidden in that. Stability alone is not enough for a fertile universe. If everything held perfectly forever, complexity would stall. If everything changed too quickly, stability would never emerge. What the cosmos seems to require is a balance between persistence and transformation. Gravity gathers, electromagnetism structures. The strong interaction binds the deep heart of matter, and the weak interaction allows selective change, the slow reworking of what has been built. It is the universe's way of permitting history at the subatomic level. This also makes it easier to appreciate why the weak interaction is so hard to notice in ordinary life. Its effects are often either hidden inside rare nuclear events or spread statistically across immense numbers of particles. You do not feel the weak interaction the way you feel a floor supporting your feet. You do not see it directly the way you see light. You infer it from decays, neutrino detections, stellar models, and the observed behaviour of matter under careful study. It asks for patience and instrumentation. It is a force for those willing to listen to whispers. Still, the whispers matter. They matter because the universe is not just a collection of bound objects sitting motionless under eternal rules. It is a world of processes. The stars shine and age. Elements are forged and transformed. Certain atoms carry within them a future change. Particles decay, neutrinos fly. Entire cosmic histories depend on these minute alterations in identity. The weak interaction ensures that matter is not merely assembled but also revised. It is the quiet mechanism by which the universe edits itself without ever becoming lawless. And yet, even as we follow this subtle unravelling, another question begins to emerge from the edges of the story. All these interactions we have discussed so far act within a deeper stage, one that is not merely empty background. Gravity already hinted at it by shaping motion and gathering worlds. But the more closely we look, the more we find that space and time themselves are not passive containers, they have structure. They influence what can happen and how things move. The universe is not only held together by forces between things, it's also given coherence by the nature of the arena in which those things exist. Because once matter can bind, radiate, gather and transform, the next mystery is the architecture that lets all of that unfold in an ordered world at all. That architecture is easy to ignore because we spend our lives inside it. Space feels like the place where things are. Time feels like the way events pass. We move through both so naturally that they seem less like part of the mystery, and more like the background against which the real story happens. A cup sits on a table in space. Tea cools over time. A train travels from one city to another. A planet circles a star. We describe all of this as though space and time are merely the stage and the actors are the interesting part. But physics, especially modern physics, asks us to slow down and be a little more suspicious of what seems obvious. Because the stage is not neutral. It is not fixed in the simple way we once imagined. And if we're trying to understand what actually holds the universe together, then sooner or later we have to ask about the architecture in which all holding and all motion take place. For a very long time, it felt natural to think of space as a kind of empty container and time as a universal clock. Space was where things happened. Time was what passed equally for everyone while they happened. This picture works well enough for daily life. If you ask when the bus arrives or where you left your keys, you do not need a revolution in fundamental physics. You need a timetable and perhaps better habits. For most human purposes, ordinary space and ordinary time behave very nicely. Rooms remain rooms. Minutes remain minutes. The earth seems steady underfoot. The sun rises and sets with a reassuring schedule, so it made perfect sense that for centuries people imagined the universe as unfolding in a fixed framework. Objects moved about, but the framework itself did not seem to participate. The problem is that nature is under no obligation to remain simple just because simplicity is convenient for creatures trying to organize cupboards and catch trains. When scientists began studying light, motion, and gravity with increasing care, something awkward began to emerge. Space and time were not behaving as independent and absolute entities after all. The measurements made by different observers, especially when they moved relative to one another or when strong gravity was involved, did not fit the old picture neatly. The deeper truth turned out to be stranger and far more beautiful. Space and time are woven together into one fabric, often called spacetime. And that fabric is not passive, it has geometry, it can be shaped, it influences motion. It helps create the order we see in the universe. This idea can sound abstract at first, and abstraction has a way of making even the most fascinating subjects feel like they are standing at a great distance with their arms folded. So it helps to bring it closer. Imagine trying to describe where and when something happens. You cannot really do one without the other. If I tell you there is a concert, that is not enough. You want to know where it is. If I tell you where it is, that is still not enough. You want to know when. Events belong to both. Your life itself is not just a path through places or a path through moments separately. It is a continuous journey through a world where location and duration are inseparable. Physics takes that ordinary fact and pushes it much deeper. It says that space and time are not simply neighbouring ideas. They are structurally linked. Once that link is taken seriously, motion becomes more interesting. We often think of motion as something an object has inside a pre-existing world. A car moves along a road. A bird moves through the air, the Earth moves around the Sun. But in a space-time view, motion is better understood as a path through this combined fabric, and not all observers agree on that path in the same way. Two people moving differently can measure time differently and disagree about distances in ways that the old picture never expected. This is not because someone is making a mistake. It is because the universe is built that way. One of the first shocks of modern physics was the realization that there is no single universal present moment, shared identically by everyone everywhere. That can feel almost rude at first. The present seems so obvious, surely now is now. But if observers are moving relative to one another, their judgments about what events are simultaneous can differ. What counts as happening at the same time for one observer may not count as happening at the same time for another. This is not philosophical wordplay. It is built into the structure of space-time. It means that the idea of one cosmic clock, ticking with perfect impartiality for the whole universe, has to be abandoned. That matters for our question because order depends on how events relate. If space and time were chaotic or inconsistent, the universe would not offer reliable structure. The very fact that physics can describe motion, interaction, causality and stability means that space-time has rules. It is not just a vague emptiness in which things wander. It is an organized framework with measurable properties. It limits what can influence what. It determines how signals travel. It shapes the sequence and relation of events. In a very real sense, part of what holds the universe together is that reality has an architecture. Light plays a central role in revealing this. The speed of light in a vacuum is not just a handy number for textbooks. It is one of the deep structural features of the universe. It acts as a kind of built-in pace limit for how information and influence can travel. No ordinary signal outruns it. That means the universe is not a place where anything can affect anything else instantly and without consequence. There is a woven order to causality. Events can influence later events only in ways that respect the structure of space-time. This gives the cosmos coherence. Causes come before effects in lawful ways. Signals have travel times. Distance matters. Timing matters. The architecture prevents the universe from turning into a kind of absurd simultaneity, where everything can jostle everything else with no regard for location or order. This also means that motion changes experience. If you travel very fast relative to someone else, time for you and time for them do not line up in the old simple sense. Clocks do not remain perfectly in agreement across all frames of motion. This is not just a thought experiment to make undergraduates frown thoughtfully into coffee. It has been measured. Time stretches and contracts depending on motion and gravity. That sounds poetic, but it is very practical. Systems such as satellite navigation depend on accounting for these differences. The universe is not pretending. Its geometry genuinely affects the pace at which time is experienced. There is something almost comforting in the fact that this weirdness remains lawful. The universe did not abandon order when it abandoned simplicity. It replaced one kind of order with a deeper one. Instead of absolute space and absolute time, we have space-time with consistent structure. Instead of a universal clock, we have locally measured times related by rules. Instead of gravity as a simple pull through empty space, we have motion shaped by the geometry of the fabric itself. It is more subtle, yes, but also more satisfying, because it explains more and fits reality better. Gravity becomes especially illuminating here. In the old picture, gravity was a force acting across space between masses. That image works beautifully for many ordinary calculations and remains useful. But the deeper account says that mass and energy affect the geometry of space-time, and that objects move according to that geometry. A planet orbiting a star is not being yanked around by an invisible rope. It is moving through a region where space-time has been shaped by the star. The path that counts as natural there is curved. So the orbit is not an arbitrary compromise, it is a consequence of the architecture. This is one reason space-time belongs in our story of what holds the universe together. It is not enough for matter to attract, bind, and transform. The arena in which it does so must also be structured in a way that preserves coherence. Imagine a universe where distances could change randomly without lawful cause, where signals could leap instantly or arrive before they were sent, where geometry had no stable relation to matter and energy. There would be no reliable orbits, no consistent causality, no predictable evolution of systems. What makes the cosmos intelligible is not only the forces within it, but the order of the stage itself. One can see this, especially clearly in orbital systems. A planet around a star is not held in place by static support. It is held in a dynamic relation. Motion and geometry together create persistence. The planet follows a path through curved space-time that can remain regular for immense spans of time. Moons do the same around planets. Stars move within galaxies. Galaxies move within clusters. Everywhere you look, order arises not from things being frozen, but from their motions being shaped within a coherent architecture. Stability in the universe often looks like movement that does not lose its form. That is a wonderful thing to remember because it runs against a common intuition. We often associate order with stillness. A tidy room is one in which everything stays put. A stable shelf is one that does not wobble. But in the cosmos, much of the deepest order is kinetic. It is order in motion. The Earth remains in its yearly path not because it is motionless, but because its motion is part of the structure. The atom remains an atom not because its constituents are frozen in old-fashioned miniature orbits, but because their allowed states form a stable arrangement. A star remains a star because competing tendencies continue in balance. The universe is not held together by stopping everything. It is held together by permitting lawful patterns of movement. Space-time also helps explain why the universe can contain both local stability and large-scale change. On the grandest scales, space itself expands. Distant galaxies move away from one another because the fabric between them stretches. And yet this does not tear apart your solar system, your planet, your teacup, or your favourite chair. Local structures held by other interactions remain intact because the expansion does not overpower those bindings at their scale. This is another sign of architecture rather than chaos. Different scales can behave differently without contradiction because the rules are layered and consistent. The universe can grow larger overall while preserving islands of order within it. This layered behaviour is one of the marks of a well-structured cosmos. The local room you sit in is not expanding in any meaningful way you would notice. The atoms in your hand are not drifting apart because of cosmic growth. The Earth is not slowly being peeled away from the Sun by the expansion of the universe. Gravity, electromagnetism, and the strong interaction maintain those structures perfectly well at their scales. But beyond those local bindings across truly vast distances, the expansion becomes important. So space-time is not just a silent container, it is active in ways that matter greatly depending on where and how you look. There's also a deep relation between space-time and causality. Causes and effects do not merely happen in some vague order, because it feels reasonable. They happen within a structure that limits what can influence what. This is one of the quiet foundations of intelligibility. If influences could propagate arbitrarily, if the ordering of events were not constrained, science would have a miserable time of it, and daily life would be even worse. The reason the universe can support memory, prediction, planning, and physical law is that events are not arranged in nonsense. Space-time has enough order to make stories possible. Not only human stories, but the stories of stars, atoms, storms, ecosystems, and galaxies. Time itself becomes more interesting in this context. It is not merely a featureless flow. Different paths through space-time can contain different amounts of experienced time. Gravity affects clocks. Motion affects clocks. What one observer measures as a certain interval need not match another observer in all circumstances, and yet this does not make time meaningless. Quite the opposite. It makes time physical. It is something woven into the world, measurable, affected by the conditions of motion and gravity, not just an invisible universal metronome clicking in the background. The architecture of order includes duration itself. This gives the universe a kind of depth that old mechanical pictures lacked. Reality is not simply objects sitting in a giant box while a master clock ticks overhead. It is a relational fabric in which matter, energy, motion, and geometry are intertwined. Space tells matter where motion can go. Matter and energy tell space how to curve. Time is part of this fabric and changes with the conditions of the journey. The result is a cosmos that is more flexible than common sense expected, and yet more tightly ordered than common sense could have guessed. There is something almost domestic about the usefulness of this realization, even though it deals with vast abstractions. Think of the difference between a room with no structure and a room with a well-built frame. In the first, nothing can reliably stay where it should. In the second, walls support a roof, doors open where expected, windows remain aligned, furniture has somewhere sensible to be placed. The architecture does not do everything, but without it, nothing else works well. Space-time is like that for the universe, though on a scale that dwarfs any house. It gives the conditions under which forces can operate consistently and motion can have form. Even black holes, which often sound like the most dramatic and destructive inhabitants of the cosmos, are in some sense extreme demonstrations of this architecture. They show what happens when space-time is curved to an extraordinary degree by concentrated mass and energy. Objects near them move in ways that would seem bizarre under old assumptions, and time itself behaves differently there. Yet black holes are not violations of order, they are expressions of it. The architecture remains lawful even in these extreme cases. Nature does not become sloppy under pressure, it becomes stranger while keeping the rules, and perhaps that is one of the loveliest features of the whole picture. The universe keeps rewarding us for taking it seriously. Each time an old, simple model turns out to be incomplete, the replacement is not chaos, but a deeper pattern. The world is not held together by crude rigidity. It is held together by subtle consistency. Motions are shaped, events are ordered, distances and durations are related in lawful ways. The stage is not passive, and because it is not passive, the actors can perform with coherence. Of course, even once we grant space-time this central role, there is still a lingering puzzle. We can now say that the universe is held together partly because the fabric of reality has structure, partly because motion happens within that structure, and partly because matter and energy shape the structure in return. But when astronomers look at galaxies and clusters and the large-scale web of the cosmos, they find that the visible matter alone does not seem to account for all the gravitational behavior they observe. Stars move as though there is more mass present than we can see. Galaxies hold together more firmly than their visible contents seem to allow. In other words, even after learning that space-time provides the architecture of order, we are left with the unnerving possibility that part of the supporting framework is still hidden from view. The universe appears to be held together not only by what is visible, but also by something dark, massive, and stubbornly elusive. That hidden support is one of the strangest turns in modern cosmology, because by the time astronomers reached it, they already had every reason to feel impressed with the visible universe. The stars were enough to occupy the imagination for centuries. Galaxies, once understood to be immense systems of stars beyond our own, expanded the scale of wonder even further. Nebulae, clusters, glowing gas, spiral arms, dark dust lanes, all of it seemed grand enough without adding another mystery. And yet, once scientists began looking carefully at how these vast structures actually move, a problem emerged that would not politely go away. The universe did not seem to be behaving as though visible matter were the whole story. Galaxies were holding together too well. Clusters of galaxies were moving as though more mass were present than telescopes could account for. The great architecture of the cosmos appeared to be supported by something unseen. This is the idea we now call dark matter, and it is one of the most important candidates for the invisible hand of the cosmos. Not invisible in a mystical sense, as though it were some supernatural layer hidden just beyond the curtains, but invisible because it does not seem to interact with light in the ordinary ways that make matter visible to us. It does not glow. It does not reflect. It does not block light in the familiar manner of dust or gas, or a wall one discovers with an unfortunate shoulder in the dark, and yet its gravity appears to matter. That is the key. Dark matter is not inferred because someone wanted to add extra mystery to an already mysterious universe. It is inferred because gravity seems to be coming from more mass than we can see. One of the earliest clues came from galaxy clusters, those enormous gatherings of galaxies bound together by gravity. When astronomers studied how fast galaxies in these clusters were moving, they found something unsettling. The galaxies were moving so quickly that the visible matter alone did not seem sufficient to keep the clusters bound. If all the mass in the cluster were just the stars and gas we could see, the system ought to be far looser, perhaps even flying apart. Instead, the galaxies behaved as though a great deal of unseen mass were helping hold the whole thing together. It was as if one had walked into a room, watched a chandelier hanging perfectly securely from the ceiling, and then discovered there was no visible chain thick enough to support it. Something hidden had to be doing the work. At first, one might reasonably suspect that the problem lay not in the universe, but in our accounting. Perhaps there was ordinary matter present that simply was not bright enough to notice easily. Maybe clusters contained vast numbers of dim stars, cold gas clouds, failed stars, blackened remnants, wandering planets, or other unobtrusive objects that could add enough mass without much light. This was not a foolish idea. The universe is not required to display all its inventory with cheerful labels, but as observations improved, it became harder to make ordinary hidden matter carry the full burden. There was simply too much missing gravity. The case became even stronger when astronomers studied individual galaxies, especially spiral galaxies. A spiral galaxy is a marvellous thing to look at even before one asks how it works. There is usually a bright central bulge, broad curving arms full of stars and gas, and a sense of organised motion across distances so vast that even language begins to feel slightly underprepared. If most of the visible mass is concentrated toward the centre, one might expect the outer stars to orbit more slowly than they actually do, much as planets farther from the Sun move more slowly than those close in. The farther out you go, the less pull from the central visible mass ought to dominate. So astronomers measured how quickly stars and gas were moving at different distances from galactic centres. What they found was deeply odd. The outer regions of galaxies were often orbiting much faster than visible matter alone could comfortably explain. Instead of dropping away in the expected manner, the orbital speeds remained high, as though the galaxies were embedded in large halos of unseen mass, extending well beyond the bright parts we can observe directly. This meant that the visible galaxy, the part full of starlight and obvious structure, might only be the luminous core of something much larger and more massive. The graceful spiral arms we admire could be living inside an enormous, mostly invisible gravitational scaffold. That word scaffold is useful because it helps us imagine the role dark matter may be playing. If ordinary matter is what makes stars, planets, gas clouds, and people who forget where they left their glasses, dark matter may be part of the larger framework within which those visible things gather and move. It does not seem to make ordinary luminous structures in the same way. It does not collapse into shining stars as readily, if at all. It appears more diffuse, more reluctant to shed energy through light, more content to influence the universe gravitationally, while refusing almost every other social obligation. And yet, by doing that one thing, by contributing mass without light, it may help shape the formation and stability of galaxies across the cosmos. A useful way to think about this is to imagine a city at night seen from a hill. The lit buildings, roads and windows tell you where life is visibly happening. But the shape of the city may also depend on infrastructure you cannot see from that distance. Foundations, buried pipes, roads in darkness, structural frames inside walls, support beams hidden behind plaster. The lighted parts are real, but they are not the whole reason the city holds its shape. In a similar way, visible matter shows us where stars burn and gas glows, but the gravitational structure behind the scenes may include far more than what shines. Dark matter would then be part of the hidden infrastructure of the cosmos. There are other lines of evidence as well. One of the most elegant comes from gravitational lensing, the bending of light by mass. Since mass shapes spacetime, light travelling near a massive object follows that curved geometry. This can distort the appearance of more distant objects behind the mass, making them seem stretched, magnified, or even multiplied into arcs and rings. By measuring these distortions, astronomers can estimate how much mass is present, regardless of whether that mass is bright or dark. Time and again, the amount inferred from lensing has exceeded what visible matter alone would suggest. In some cases, the mass appears distributed in ways that strongly indicate a large unseen component. The universe, in effect, has been giving us a gravitational map of its hidden matter. This becomes especially striking in collisions between galaxy clusters. When clusters pass through one another, different kinds of matter can behave differently. The hot gas in the clusters, which is ordinary matter, can collide and slow down. But much of the gravitational mass inferred from lensing seems to pass through more cleanly, remaining offset from the slowed gas. This suggests that the dominant unseen mass is not behaving like ordinary luminous gas. It does not seem to interact strongly with itself or with normal matter except through gravity, at least not in the ways that would cause obvious slowing and heating. That is one reason dark matter remains such a compelling idea. It helps explain not only that extra mass seems present, but also how that mass behaves. There is also the larger scale pattern of cosmic structure itself. The universe is not arranged randomly. Galaxies gather into clusters, clusters into larger filaments and walls, with great voids between them. It is a kind of cosmic web, magnificent in scale and intricate in pattern. Computer simulations that include dark matter do a much better job reproducing the large-scale structure we observe than those relying only on ordinary visible matter. The hidden mass seems to provide an early gravitational backbone, encouraging matter to clump and structure to grow in the ways the cosmos appears actually to have chosen. In that sense, dark matter is not only helping hold galaxies together now, it may have been crucial in helping them form in the first place. This is one of the reasons dark matter fits so naturally into our broader question. What is actually holding the universe together? Not in the deepest nuclear sense, not in the chemical sense of everyday objects, not in the orbital sense of planets around stars alone, but in the larger architecture of galaxies and clusters. Here dark matter may be part of the answer. It is not visible glue. It is not an all-purpose substitute for every mystery, but it seems to add the gravitational heft needed for structures to endure and develop on scales where visible matter by itself looks insufficient. Of course, there is an important humility built into all of this. Dark matter is a name for something inferred, not a finished explanation. It tells us that there appears to be extra mass behaving in certain ways, but it does not yet tell us exactly what that mass is. That distinction matters. Sometimes in science, a name can create the comforting illusion that a mystery has been solved, when in fact it has only been described more carefully. Calling it dark matter does not magically reveal its identity any more than calling an unknown house guest the fellow in the hallway tells you where he came from, or why he is carrying your umbrella. The term is useful, but it is also a marker of ignorance dressed in good manners. Many possibilities have been proposed over the years. Some ideas focused on faint ordinary objects, such as dim stars, black holes, or other compact bodies too hard to detect in large numbers. These possibilities have not vanished entirely from discussion, but they do not seem able to account for all the missing mass required by observations. The leading possibilities generally involve new kinds of particles not yet directly detected in the laboratory. These hypothetical particles would have mass, would interact only very weakly with ordinary matter and light, and would therefore be extremely difficult to catch. They would pass through much of the visible universe almost unnoticed, contributing gravity while otherwise minding their own business with extreme determination. There is something almost mischievous about that. The universe may contain a dominant form of matter that neither glows nor absorbs light nor bumps into ordinary atoms in familiar ways, and so has remained hidden from direct view while still shaping the cosmos around us. It is as though one had spent years admiring the arrangement of leaves in a garden, only to discover that most of the landscaping budget went into invisible retaining walls underground. The visible world begins to look less complete, less self-sufficient, and much more interesting. If dark matter is real in this particle sense, then your room, your planet, your body, and the visible stars around you are not made of the most common kind of matter in the universe. That is a slightly unsettling thought. We tend to imagine ourselves as built from the basic stuff of existence, but ordinary matter, the kind that makes atoms, chemistry, food, oceans, lungs, libraries, and socks that somehow never return from the wash in matching pairs, may be only a minority component of the cosmic matter budget. The dominant mass in galaxies could belong to something far stranger and quieter. We would then be living not in a universe made mostly of familiar stuff, but in one where familiar stuff is a luminous exception drifting inside a much larger invisible framework. This does not make ordinary matter unimportant, of course. Stars still shine, planets still form, chemistry still matters enormously. But it does change the emotional balance of the cosmos. The visible is no longer obviously the substantial. The bright parts are not necessarily the heaviest parts. What you can see is not all that can hold. In some ways, that is a recurring lesson in physics. The deepest supports are often hidden. The chair feels solid because of invisible electromagnetic structure. The atom holds because of hidden interactions in its nucleus. The galaxy may endure because of unseen mass in a vast halo. Again and again, the universe tells us that apparent simplicity is supported by concealed complexity. There is another intriguing aspect to dark matter. Because it does not seem to interact strongly with light, it also would not cool and collapse the way ordinary gas does. Ordinary matter can radiate energy away, which lets it settle into thinner, denser structures such as disks, clouds, stars, and planets. Dark matter, by contrast, appears to remain more puffed out, more halo-like, less inclined to gather into the compact luminous objects that dominate our telescopic imagination. This helps explain why galaxies might have bright visible disks embedded inside larger diffuse dark matter halos. The two kinds of matter play different roles because they follow different rules of interaction. That layered structure is pleasingly consistent with much of what we have seen already. The universe uses different tools at different scales. The strong interaction binds nuclei. Electromagnetism shapes chemistry and light. Gravity gathers worlds and galaxies. Dark matter, if we have understood it correctly, adds hidden mass and hidden scaffolding to the larger structures. The cosmos is not held together by one simple substance or one single trick. It is held together by a hierarchy of influences, each doing its work where it is most effective. And yet there remains a note of tension in the story, because dark matter is still inferred rather than fully captured. Detectors have been built in deep underground laboratories, shielded from noise and cosmic interference, waiting for the faintest possible sign of a dark matter, particle brushing past ordinary matter. Astronomers keep searching for indirect hints in cosmic rays, gamma rays, and the large-scale behavior of galaxies. Particle physicists test theories, revise models, and continue the hunt with admirable stubbornness. It is one of the great ongoing scientific pursuits of our time. We know something about what dark matter must do if it is there. We know less about what it is in itself. The invisible hand remains gloved. This uncertainty has led some scientists to ask whether the missing gravity points not to unseen matter, but to a need to revise our understanding of gravity itself on galactic scales. That is a serious idea, and not merely the scientific equivalent of flipping the table when the puzzle becomes annoying. If observations do not match theory, one must consider whether the inventory is incomplete or the rules are incomplete. Modified gravity ideas attempt the second route. They seek to explain galactic motions without as much unseen matter. Some have had partial successes in specific contexts. But dark matter remains the broader and more widely used framework because it appears to explain a wider range of evidence across clusters, lensing, structure formation, and the cosmic web. Still, the existence of alternatives is healthy. Science progresses not by falling in love with a single answer too early, but by testing whether that answer survives competition. There is a certain elegance in the possibility that galaxies are held together by something that does not announce itself through light. It fits a pattern we have already encountered more than once. The visible world is often a surface expression of deeper hidden order. The stars are what you notice, but the mass that shapes their orbits may be mostly unseen. A spiral galaxy then becomes not just a collection of shining stars, but a kind of luminous embroidery stitched into an invisible gravitational garment. The bright arms are real, but they are not the whole structure. They are what the structure allows ordinary matter to become, and perhaps that is why dark matter feels so compelling even before it is fully understood. It extends our central question in exactly the right way. What holds the universe together is not always what glows, not always what can be photographed directly, not always what seems most obvious to the senses. Sometimes the support lies in a hidden layer, inferred by motion, by bending light, by the persistence of structure over immense distances. The universe may be full of unseen mass quietly doing the work of cohesion, while visible matter takes the applause. Still, for all its gathering power, dark matter belongs on the side of gravity and structure. It helps things clump. It helps galaxies stay bound. It favours formation, scaffolding, and persistence. But when astronomers looked even farther outward, at the largest fate of the universe itself, they discovered something almost opposite in character. Space was not merely expanding, the expansion appeared to be speeding up. The cosmos, instead of slowing under gravity's great collecting influence, seemed to be pushing outward ever more strongly. So even as one hidden ingredient appears to help hold vast structures together, another hidden influence seems to be loosening the larger fabric, or at least stretching it with growing insistence. And that means the next turn in the story is not about unseen matter that gathers, but about whatever it is that makes the universe push back. That outward insistence changed the mood of cosmology in a very deep way, because for a long time it seemed reasonable to imagine that gravity would have the last word. The universe might expand, certainly. That much had already become clear once astronomers began measuring the motion of distant galaxies. Space itself was not static. The cosmos was not a fixed grand hall with galaxies neatly placed inside it forever. It was growing, stretching, carrying large-scale structures away from one another over time. But even then, one could still imagine a future in which gravity gradually slowed that expansion. After all, gravity gathers. Gravity resists dispersal. Gravity turns clouds into stars and keeps galaxies bound. Surely, given enough time, the great mutual pull of all matter might begin to rein in the cosmic drift. That expectation was not foolish. In fact, it was the natural one. If you throw a ball upward from the ground, it rises, slows, and then falls back. If two masses attract one another, distance works against easy escape. So when cosmologists thought about the expanding universe, many imagined that the expansion should be decelerating under the pull of all the matter within it. The interesting question seemed to be how much deceleration there was. Perhaps the universe would expand forever, but more and more sluggishly. Perhaps it would reach some delicate balance. Or perhaps gravity might eventually win so thoroughly that the expansion would reverse and the cosmos would begin contracting. Those were the kinds of endings people debated. What very few expected was that the universe was not simply coasting outward, nor merely resisting a slowdown with stubbornness, but accelerating. The expansion itself appeared to be picking up pace. That discovery was one of the great shocks of modern astronomy, because it did not merely add a detail to the story, it changed the emotional structure of the whole tale. Until then, expansion had still felt compatible with an eventual triumph of gathering. But an accelerating expansion suggests something else at work. Not just matter and gravity, not just inertia and the aftermath of the early universe, but some large-scale influence that behaves in a way almost opposite to ordinary attractive gravity. Something that does not help hold cosmic structures together, but instead increasingly stretches the space between them. If dark matter seemed to provide hidden support for galaxies and clusters, this new ingredient seemed to act as a hidden pressure towards separation. It was as though the universe, having spent billions of years assembling stars, galaxies, planets, and all the rest, had also built into itself a long-term tendency to loosen its own architecture. To understand why this matters, it helps to be very clear about what cosmic expansion actually means. It does not mean that galaxies are flying through pre-existing empty space from a single central explosion point in the ordinary sense. There is no obvious cosmic middle from which everything is fleeing like startled pigeons after a dropped sandwich. Instead, the best way to think of it is that the large-scale fabric of space is stretching. Distances between faraway galaxies increase not because they are racing through a static void in the way a bullet crosses a room, but because the room itself, if one may push the image much farther than any carpenter would recommend, is growing between them. This distinction matters because it helps explain why local things do not get pulled apart by expansion in any ordinary way. Your body is not expanding. Your room is not quietly inflating while you sleep. The Earth is not drifting away from the Sun because of cosmic expansion, at least not in any meaningful everyday sense. Local systems held together strongly by gravity, electromagnetism, or the strong interaction remain intact. A galaxy can stay bound. A solar system can remain loyal. A table can continue to be wonderfully table-shaped. Expansion dominates where matter is thinly spread over immense distances, and where no stronger local binding overcomes it. In other words, the universe can push outward overall while still preserving islands of order inside it. That is already a subtle enough picture. But acceleration takes it further. It says that on the larger scales, the stretching of space is not merely continuing as a relic of ancient beginnings, it is becoming more influential over time. This was discovered by studying very distant stellar explosions called Type I supernovae, which can serve as cosmic distance markers because their brightness follows a predictable pattern. By comparing how bright these explosions appeared with how much their light had been stretched by cosmic expansion, astronomers could infer how the expansion had behaved over time. The result was startling. Far away, supernovae looked dimmer than expected in a way that suggested the universe had expanded more than a simple decelerating model would allow. The cosmos, it seemed, had not been putting on the brakes. It had been pressing the pedal. Once you accept that, a new question arrives immediately. What could cause such behaviour? Matter with ordinary gravity pulls inward. Radiation contributes to the energy content of the universe, but it does not produce this kind of late-time acceleration in the needed way. Something else seemed required. The name given to this unknown influence is dark energy, and like dark matter, the name is useful but incomplete. It identifies a problem with admirable dignity. It does not solve it. Dark energy is what we call the mysterious large-scale influence associated with the accelerated expansion of the universe. whether it is a property of empty space itself, a new field spread through the cosmos, a sign that gravity behaves differently on the larger scales, or something else not yet imagined clearly enough, remains one of the great open questions in physics. There is a beautifully unsettling irony in the idea that empty space itself might not be truly empty. We tend to imagine vacuum as nothing, as absence, as the clean stage left behind when all the actors have gone home. But modern physics has long warned us that the vacuum is not so simple. Even in quantum theory, empty space has structure and restless possibility. Fields remain, fluctuations matter, the vacuum may have energy associated with it. If space itself carries a kind of intrinsic energy, and if that energy has the right large-scale gravitational effect, then the expansion of the universe could accelerate. In that case, the very emptiness between galaxies would become an active participant in cosmic history. Not merely a passive gap, but a driver of separation. One of the oldest and most elegant ways this can be expressed is through the idea of a cosmological constant, a term that can be added to the equations of general relativity to represent a uniform energy density associated with space itself. This idea has a curious history. It was introduced long before accelerated expansion was observed, for reasons tied to the possibility of a static universe. Later it was often treated almost as an embarrassment, a mathematical extra that nature had declined to use. Then the expanding universe was established, and the need for a static model vanished. But when acceleration was discovered, the old idea returned, looking suddenly relevant and annoyingly vindicated. If empty space has an energy density that remains roughly constant as the universe expands, then as matter becomes more dilute over time, this vacuum-like influence can come to dominate the large-scale behavior of the cosmos. Matter thins out. Empty space does not stop being empty, and its effect remains. There is something almost comically audacious about that. The more space there is, the more of this vacuum-related effect there would be overall, because there is simply more space in which it is present. So the universe expands, creating more space, and the large-scale outward tendency associated with that space continues to matter. It is not hard to see why this leads to acceleration. The large-scale future begins to belong not to clumping matter alone, but to the deep properties of space-time itself. Still, one must be careful not to become too fond of any one interpretation too quickly. Dark energy may indeed be a cosmological constant, a built-in property of the vacuum, but there are other possibilities. Perhaps the influence changes over time. Perhaps it comes from some field not yet fully understood. Perhaps our theory of gravity, though extremely successful, needs adjustment on the larger scales. This is one of those regions where modern cosmology becomes both precise and humble at once. We have strong evidence that the expansion is accelerating. We can model the universe very successfully by including a dark energy component. But the underlying nature of that component remains uncertain. We know what the universe appears to be doing. We know less securely why. That uncertainty makes dark energy different in tone from many of the other things we have discussed. The strong interaction is strange, but its role in nuclei is clear. Electromagnetism is everywhere, and we know its daily handiwork very well. Gravity remains profound, but its effects are familiar across scales. Dark matter, though still unidentified in substance, at least behaves as a gathering influence through gravity. Dark energy is more disorienting. It is not just unseen. It is conceptually slippery. It acts not by building structures but by affecting the fate of structures through the expansion of space itself. It is less like hidden scaffolding, and more like a hidden drift in the floorboards of the cosmos. So what does this mean for the limits of holding on? It means that the universe is not arranged as a simple triumph of cohesion. For all the remarkable ways matter can gather, bind, orbit, and persist, there are scales at which separation gains the upper hand. Galaxies can remain bound internally while moving farther from other galaxies. Local clusters can stay coherent while the space beyond them stretches ever more quickly. Over immense timescales, regions of the universe may become increasingly isolated from one another, not because their contents fail locally, but because the fabric between them continues to expand. The cosmos in that sense may become more lonely even while its internal structures remain for a time intact. This leads to one of the more haunting visions of the far future. If accelerated expansion continues indefinitely in a manner similar to what we currently observe, then distant galaxies beyond our local gravitational neighbourhood will move ever farther away. Their light will become more stretched, more faint, harder, and eventually impossible to observe. Future astronomers, if any exist in such a distant era, might look out from their galaxy and see far less evidence of the wider cosmos than we can see now. The observable universe would shrink in practical richness, not because the rest had ceased to exist in some absolute sense, but because it had receded beyond the reach of signals. The great cosmic web would fade from view, leaving isolated islands of bound matter surrounded by emptiness that no longer tells its history. There is something deeply instructive in that prospect. It reminds us that what can be held together depends on scale and on the competition between influences. A galaxy can resist internal dispersal because gravity and perhaps dark matter hold it together. A solar system can remain bound within a galaxy. A planet can circle its star. Chemistry can continue. Life, if conditions allow, could persist locally. But the larger relational structure between such systems may be steadily undone by expansion. Holding on has jurisdiction. It is powerful, but not unlimited. The universe seems to permit strong local order within an ever-widening larger separation. Of course, there are more dramatic possibilities people sometimes discuss. If dark energy were not constant but grew stronger over time in a particular way, then one could imagine a far future in which even bound systems might eventually be overwhelmed. Galaxies could be torn apart, then solar systems, then planets, then atoms themselves. This idea, sometimes called a great ripping apart, belongs to the more speculative end of cosmological futures. It is dramatic, memorable, and slightly too fond of itself, which perhaps explains why it appears so often in popular treatments. Current evidence does not require such an extreme fate. A more measured and still sobering picture is that accelerated expansion continues, local systems remain bound, but the universe grows colder, darker, and more isolated over unimaginable timescales. That quieter outcome is often associated with the idea of heat death, though the phrase can sound more violent than the process really is. It does not mean flames or collapse or a sudden cosmic disaster. It means a future in which usable energy gradients become rarer, stars eventually exhaust their fuel, galaxies age, matter settles into longer and quieter forms, and the universe approaches a state of greater overall uniformity and less dramatic activity. It is the large-scale consequence of a cosmos where expansion continues and entropy increases. Not everything flies apart in a theatrical tantrum. It simply becomes harder and harder for new structured events to occur on the grand stage, and yet even here it is important not to lose sight of timescale. These futures lie so far beyond ordinary imagination that even the phrase billions of years soon begins to feel like pocket change. Stars like the Sun live for billions of years. Larger cosmic transformations stretch beyond that by huge factors. The limits of holding on are real, but they are patient. The universe does not usually trade in abrupt endings. It trades in long transitions, in structures gradually losing dominance, in balances slowly shifting. If one wants melodrama, the cosmos occasionally provides supernovae and black holes. But much of its deepest history is written in slow handwriting. There is also a philosophical temptation here, and it is worth resisting the worst versions of it while enjoying the better ones. The fact that the universe may not hold itself together forever on the larger scales does not mean that structure is somehow futile or unreal. Quite the opposite. The very richness of stars, planets, chemistry, biology, and thought depends on the existence of long periods where holding together works magnificently. Temporary does not mean trivial. A galaxy that endures for billions of years is not a failed structure because it does not last forever. A star that shines steadily long enough for life to arise on one of its planets has done something extraordinary, even if cosmology refuses to guarantee eternal tenure. Perhaps this is part of what dark energy teaches us most quietly. The universe is not simply a monument to cohesion. It is a negotiation between cohesion and release. Gravity gathers, dark matter supports, electromagnetism shapes. The strong interaction binds, the weak interaction allows change. And on the larger scales, dark energy appears to stretch the arena itself, placing limits on what gathering can achieve globally. Reality is not held together by one victorious principle. It is composed by competing tendencies, each with its domain, each with its timescale, each contributing to a world where order exists but does not claim the whole field forever. This gives the cosmic story a kind of maturity that I rather like. It would be easy to imagine a universe that was all togetherness or all dispersal, all permanence or all decay, all gathering or all release. But ours seems more balanced than that. It permits local bonds of astonishing strength. It permits great structures like galaxies and clusters. It permits long histories, complex chemistry, and the patience needed for living things to appear. And at the same time, it does not allow any of this to become absolute at every scale. The larger fabric remains dynamic. Expansion continues. Distances grow. The cosmos keeps some of its cards very close to its chest. There is something almost intimate about the fact that we live in a moment when the universe still reveals so much of its large-scale history to us. We can still see distant galaxies. We can still observe relic light from the early universe. We can still infer expansion, structure formation, dark matter and dark energy from a sky that has not yet hidden its evidence behind too much distance. That makes the present epoch, in a cosmological sense, rather special for curious creatures. The universe is still legible enough to tell us what it has been doing. It has not yet stretched its great autobiography entirely beyond the horizon. And so we arrive at a slightly paradoxical understanding. The universe is held together in countless ways, but not without limit. The same cosmos that builds stars and galaxies also expands in a manner that prevents total reunion. The same reality that encourages matter to bind also allows the large-scale fabric to stretch. The result is not contradiction, but layering. Different rules dominate in different places. Different futures apply to different structures. What can hold depends on what is trying to separate it, and on what scale the contest is taking place. That in turn leaves us with the final and perhaps most human version of the whole question. After all the forces and particles and hidden mass and expanding space-time, what does it really mean to say the universe stays together at all? Is togetherness just a technical matter of binding energies and orbital stability? Or is there a deeper lesson in the fact that order can emerge, persist, and carry meaning even in a cosmos that does not promise permanence everywhere forever? Because once we have followed the invisible supports from atoms to galaxies, and from gravity to dark energy, the last step is not just to list what holds things together, but to ask what kind of togetherness the universe is actually offering. By the time we arrive here, the question has become both simpler and deeper than it first appeared. What does it really mean for the universe to stay together? At the beginning, it may have sounded like a question about glue on the grandest possible scale. As if somewhere behind the stars there might be a single answer, one master force, one invisible hand gripping everything tightly enough to stop it from drifting into chaos. But the longer we have sat with the problem, the clearer it becomes that the universe is not held together by one thing. It is held together by layers of order, by different kinds of persistence at different scales, by a set of relationships that allow matter, motion, and time to form lasting patterns, And perhaps most important of all, it is held together not by permanence in the absolute sense, but by stability that lasts long enough for history to happen. That last part matters more than it may seem. When people ask what holds the universe together, there is often an unspoken hope behind the question. We want togetherness to mean security. We want it to mean that reality is firm beneath us, dependable, well assembled, immune to absurd collapse. And in many everyday ways that is true, the floor supports you. The Earth keeps its orbit. Atoms do not suddenly lose interest in being atoms while you're making tea. The world is dependable enough that you can build a life inside it without checking every morning whether chemistry has resigned. But physics also teaches something gentler and more honest. Staying together does not mean standing still forever. It does not mean being immune to change. It means that the universe contains arrangements that can endure, patterns that can persist, systems that can hold their shape while still participating in time. That is a very different kind of togetherness than the one our first intuition might suggest. A mountain remains a mountain for a long time, but not forever. A star remains a star for an astonishingly long time, but not forever. An atom may endure almost indefinitely under ordinary conditions, while a radioactive nucleus changes when the moment is right. A galaxy can remain bound for billions of years even as the universe expands around it. So togetherness in physics is not a promise of eternal stillness. It is the achievement of continued form within a changing world. In some sense, that makes the universe more impressive, not less. A cosmos where nothing ever changed would be easy to describe but difficult to admire. It would not need much explanation because it would not do very much. A cosmos where everything dissolved instantly would be dramatic but barren. There would be motion, perhaps, but no real history, no structure lasting long enough to build on itself, no stars patiently making heavier elements, no planets cooling, no chemistry growing complicated enough to think about chemistry. What makes this universe remarkable is that it permits a middle condition. It permits processes that hold long enough to create richness, and it permits change enough to keep richness from becoming impossible. That middle condition appears again and again across all the scales we have visited. The strong interaction holds the atom's heart together. Electromagnetism shapes atoms into molecules and matter, into the ordinary world. Gravity gathers gas into stars and binds planets to suns and galaxies to themselves. Dark matter, if our best current picture is right, provides additional hidden support for the large-scale architecture of galaxies and clusters. Even space-time itself contributes by providing a lawful structure in which motion, causality and duration can make sense. And then, against all of this gathering and binding, there are also the forces and tendencies that loosen, stretch, transform, and unravel. The weak interaction allows matter to change identity. Entropy pushes systems toward more spread-out states. Dark energy appears to stretch the large-scale fabric of the cosmos ever more insistently. The universe stays together not because dispersal is absent, but because dispersal and cohesion are in constant conversation. That is perhaps the deepest correction physics offers to ordinary intuition. We tend to imagine order and disorder as opposites in the simplest possible way, as though one must defeat the other completely. But nature is usually subtler than that. Order can exist locally even while disorder increases globally. A star can shine in a universe where entropy is growing. A living body can maintain structure by exchanging energy and matter with its surroundings. A galaxy can remain bound inside an expanding cosmos. Stability is not the cancellation of change. It is a way of participating in change without immediately losing form. And that is where the phrase "stay together" begins to take on a more mature meaning. It does not mean frozen. It does not mean final. It does not mean exempt from history. It means coherent. It means that a thing can remain itself across time well enough to have a story. A planet has a story because it remains a planet long enough to cool, to gather an atmosphere or lose one, to be struck, reshaped, weathered, perhaps inhabited. A star has a story because it remains a star long enough to pass through stages, forge new elements, alter the worlds around it, and eventually become something else. Even a human life has a story for the same reason. Not because the body is static, since it very much is not, but because the pattern remains continuous enough for memory, growth, injury, healing, learning, and love to make sense. Togetherness is continuity with room for change. Seen that way, the universe is less like a machine made of rigid parts and more like a layered system of durable patterns. Some of those patterns are so small we only find them by splitting matter apart and listening carefully to what the fragments tell us. Some are so large they require whole observatories, satellite missions, and patient decades of measurement. But the same broad truth appears at every level. Reality permits arrangements that last. Those arrangements are never supported by nothing. They are supported by laws, balances, and relationships. They are held not by a single hook, but by a structured web of conditions under which persistence is possible. This has a practical consequence for how one sees the world. A stone is no longer just a stone. It is a successful arrangement of atoms held in a lattice by electromagnetic structure, resting on a planet made round by gravity, orbiting a star held together by the pressure and fusion of its interior within a galaxy likely supported in part by unseen mass, inside a universe whose expansion is shaped by properties of space-time that remain only partly understood. None of this makes the stone less ordinary. In fact, it makes its ordinariness more admirable. The everyday world stops looking simple in the dismissive sense and starts looking simple in the elegant sense. Familiar things are familiar not because they are shallow, but because the universe is astonishingly good at making complexity feel natural. There is also a lesson here about scales. One of the reasons the question felt so difficult at first is that it asks for one answer to many different problems. What holds a nucleus together is not what holds a molecule together. What holds a molecule together is not what holds a planet in orbit. What helps keep a galaxy bound is not what allows a protein to fold. The universe is not badly designed because it uses different strategies at different sizes. Quite the opposite. That is one of its strengths. Different scales require different rules to dominate. A well-built city does not use the same materials and techniques for teacups, bridges, door hinges, and drainage systems. Neither does nature. It has local specialists and large-scale organizers. The world works because the right kind of order appears where it is needed. This is why the dream of one single image that explains everything at once is often so tempting and so misleading. People want a picture of reality where all togetherness is one kind of togetherness, where all support can be described with one metaphor, one sentence, one mental image sturdy enough to survive every scale. But nature seems more interested in coherence than in oversimplification. It gives us unity through laws, yes, but also variety through their consequences. The universe is one world but not one texture, one history but not one mechanism, one fabric but not one stitch. And yet there is a deeper unity after all. It does not come from one force doing all the work. It comes from the fact that all these different kinds of holding together belong to the same lawful reality. The atom and the galaxy are not unrelated miracles. They are different expressions of one universe. The same cosmos that allows quarks to bind also allows stars to form. The same physical order that produces chemical bonds also gives rise to light, time, gravity, and cosmic structure. That unity is not simple in the childish sense, but it is profound. It means the world is not patched together from incompatible pieces. It is varied, but it hangs together intellectually as well as physically. There is a reason we can tell one story from the very small to the very large. The story changes tone and scale, but it never leaves the same universe. This is also where the question becomes slightly more human. Because once we understand that the universe stays together through layered forms of order, we start to notice that our own lives exist inside one of the narrow windows where many kinds of stability happen to overlap beautifully. The Earth remains in a long-lived orbit around a stable star. The chemistry of matter is rich enough to build cells. The temperature range on the planet allows liquid water. The atoms in our bodies are stable enough to make memory and metabolism possible, yet flexible enough to participate in living change. Day follows night. Seasons return. Gravity is strong enough to keep us grounded, but not so strong that movement becomes misery. Electromagnetism allows solid objects warm fires, sunlight, and the nervous systems by which we sense all of it. This is not a sentimental point. It is a physical one. We live inside a particularly successful pocket of cosmic togetherness. That pocket is not eternal, of course. No serious look at the universe allows one to keep that illusion untouched. Stars age, planets change, species are brief, galaxies collide, expansion continues. Even the most stable structures have conditions under which they fail. But the lesson is not that nothing holds. The lesson is that holding is real even when it is not endless. A bridge does not become meaningless because it will one day rust. A song does not become worthless because it ends. A star does not become trivial because it has a life cycle. Duration matters, but infinity is not the standard by which meaning or physical success must be judged. The universe offers finite stability, and finite stability turns out to be enough for astonishing things. That may be why the question feels bigger than physics alone, even though physics gives the clearest answer. What holds the universe together, in the scientific sense, is a layered set of interactions and structures that create persistence across scales. But what it means for the universe to stay together is that there can be continuity without rigidity, change without total collapse, and order without the false comfort of permanence. The cosmos does not promise that every structure will last forever. What it provides instead is a world where lasting is possible, where form can emerge and remain long enough to matter. And if you step back from the details for a moment, that is an extraordinary arrangement. Think of how many things had to be true for there to be a night sky at all, for stars to form and burn, for atoms to endure, for matter to bond, for gravity to gather, for time to have direction, for life to exist on one small world, and ask whether any of this is held together. The answer is not that the universe has one secret clasp hidden behind the curtain. The answer is that reality is built to support structure. Not structure everywhere equally, not structure forever, and not structure without tension, but enough structure for complexity to arise, and enough stability for that complexity to continue. That continuation is easy to overlook because we are used to it. We wake each day inside a world that has not come apart. The sun rises with immodest reliability. Water still behaves like water. Stones remain unpersuaded by human opinions. The moon has not resigned from its post. All of this can feel ordinary. But ordinary is often just a word for miracles that have become routine. Physics does not remove that feeling, it sharpens it. It tells us why the routine works, and in doing so makes the routine more astonishing. Perhaps that is the most satisfying place to end up, not with a single grand slogan, but with a better kind of understanding. The universe stays together because the laws of nature allow stable patterns to exist at every scale, from nuclei to stars to galaxies. It stays together because forces gather, bind, structure, and regulate change. It stays together because space-time has an architecture, because matter has properties, because history unfolds under rules rather than nonsense. It stays together because even in an expanding and changing cosmos, there are islands of persistence where order can flourish. And it stays together in the human sense because all of that physical continuity adds up to a world where moments can connect to other moments, where causes lead to effects, where memory can refer to something real, and where tomorrow usually belongs to the same universe as tonight. So if you were to ask once more, very gently now, what is actually holding the universe together, the answer would be something like this. Not one force, not one object, not one final hidden screw behind the stars. It is held together by relationships, by gravity drawing mass into lasting structures, by electromagnetism giving matter form and chemistry, by the strong interaction binding the deep core of matter, by the weak interaction allowing controlled change, by dark matter shaping large-scale scaffolding, by space-time providing a lawful arena for motion and causality, and by the fact that all of these coexist in ways that let order survive. And maybe there is a quiet comfort in that. The universe is not held together by stubbornness alone. It is held together by balance, by cooperation between very different rules, by the possibility that reality can be dynamic without becoming incoherent, which is perhaps why it feels so natural after all this to look around your own little corner of the cosmos with slightly renewed respect. The room you are in, the air you are breathing, the floor beneath you, the star beyond your roof, the galaxy carrying that star, all of it is part of the same long success story of things managing, against many odds and through many changes, to remain themselves for a while, and for now, tonight, that while includes you. You're here in one stable pocket of a very large and restless universe, held by gravity to a turning world, held by chemistry in the shape of a living body, held by memory inside a continuous life, listening in your own small region of space and time while the great structures of reality quietly continue their work around you. The universe may be vast, layered, and in many ways unfinished in our understanding of it, but it is not falling apart all at once. It is, in countless visible and invisible ways, still holding. And perhaps that is enough to let the mind soften a little, to let the question rest where it belongs for now, not answered in one sentence, but understood in a deeper one.